Hold on, okay. I can start? Maybe I have to share. Is there a Zoom? No, I have to share. No, it's okay.
C'est avec un canal de YouTube.
Ok.
Pour la transmission.
Okay. So I can start. Buenos dias. So I'm going to present the lecture about the gene therapy. So gene therapy is part of what we call advanced therapy medicinal product. So we are belonging to this ATMP product. We have gene therapy, but somatic cell-based medical product, tissue engineering product, and what we call combined ATMP, for instance, when we can mix a sort of mix between gene therapy and cell therapies. Gene therapy is the use of acid nucleic as pharmaceutical agent to treat disease. It derives its name from the idea that DNA can be used to supplement or alter, can supplement, replace, modify altered genes. And then the altered gene. Different modalities of gene therapy are used. For instance, for product delivery, if you have ex vivo, that means that genetically modified cells are injected to the patient to treat it. That's called ex vivo because the cell is modified and genetically ex vivo and administered to the patient. Otherwise, it's in vivo. For instance, when a viral vector is administered directly to the patient, sometimes in the organ. And we can use various delivery tools. I said vector, but it could be a viral vector, a non-viral vector. So there are, this is just for a few words about regulation. It's gene therapy are biological products. They are genetically modified organisms that have been used or created. As I said before, they are called advanced therapy medicinal products, and they are regulated according to international guidelines and regulation. In a snapshot, it's still gene therapy is still largely experimental. You have a lot of research in a lot of basic research on different laboratories in the world. About 2,000 gene therapy products are in development in laboratory, academic, for instance. You have several hundred clinical trials in men ongoing around the world. About 33 gene therapy products receive marketing authorization today. And 1/3 of the authorized products are chimeric antigen receptor T cells. We have several diseases who are treated by can be treated by gene therapies. Cystic fibrosis, hemophilia, so for example, sickle cell disease, muscular dystrophy, as well as Leber's congenital amaurosis. I will explain a little bit later on what is Leber's congenital amaurosis and the principle of the treatment. When we perform gene therapy approaches, we have a different possibility. It could be a gene addition, that could be gene silencing, so to block the expression of the gene, or to correct or to modify the mutated genes. Otherwise, or sometimes it's to add a new gene. You have different possibilities. But when we perform gene therapy, we have to keep in mind that the nucleic acid has to be bring into the cells. So how you bring the nucleic acid on the cells and how it enter in the cells. So that's the problem is that the cells are protected. The cell membranes are usually negatively charged. It's the same for the DNA. So that's why when we try to transfect naked DNA, that's not efficient. Another possibility is to perform a transfection complex by using calcium phosphate that will produce, it will precipitate with DNA, and the precipitate will interact with the membrane cells, and then triggering an endocytose mechanism and allowing the DNA to enter in the cells. But it's not the most use method. Otherwise, you have the lipid molecular complex containing DNA, RNA, or protein. I will go fast because Hervé will develop that later. The last possibility is use the viral vectors, which is the most widely used at the moment. And in this case, the biological property of the virus are exploited to allow the DNA to enter in the cell. So because we know that the virus has the ability to enter into the cell and to integrate his genome in the genome of the cell. That's why it's very useful. What he's tried to do is to use a non-pathogenic virus. That's why the virus is himself genetically modified and generally non-replicative. In this slide, it's a summary of all the vectors used in gene delivery. So you have two types of vectors, viral vector and non-viral vectors. For the viral vectors, the most used are adenoviral vector. We have the first gene therapy approved in China was adenoviral vectors. Retrovirus and lentivirus or adeno-associated virus. That's the three most used virus. Among the non-viral vectors, you have the lipid-based system. I leave this to Hervé. Or the physical method. Just a few words at the end of this lecture, but they can use needle injection to administrate or microinjection to administrate directly the DNA in the cell, or electroporation, sonoporation, for instance, by using a sound pulse or electric pulse to create a pore in the membrane of the cell, allowing the DNA to enter. So when you are thinking about gene therapy, you have to ask yourself this question: how I can choose my vector toolbox? Which kind of toolbox I'm going to use? Virus one or non-virus one? What we know is that virus and non-viral tools enable various strategy to allow the DNA to enter in the cells. So we have, and we can perform gene transfer, mRNA transfer, gene editing. Non-virus vectors are less complex to produce than viral vectors. That's why they become more and more popular. But for the moment, the expertise, the best expertise, I would say, or the best experience is concerned the viral vectors. We have to consider as well when we choose the vector toolbox, what is the mode of mechanism of action we need? Is it a gene addition, a gene editing, or suppress a gene? What is the tissues? Because we know that some viral vectors has a preferred tropism for organs, for different organs. What is the modality? As I say, ex vivo with a modified cell administered to the patient, or in vivo directly in the organs. And what is the production complexity? Is it easy or not to produce this viral vector, which is another question. So when we talk about gene therapy, we have to think about gene transfer, which is a major challenge of this kind of therapy. So the gene transfer can be what we say permanent when the gene transfer is integrated in the cellular genome, and then when the cell is divided, you will find the gene of interest integrated in the genome of the daughter cells, let's say. Otherwise, in a lot of cases, it's called episomic, so it's outside the genome, and when the cell is divided, the episome will be transferred only to one cell and not to the other. So there is two possibilities. So the most commonly used gene therapy vectors, especially for gene transfer, are the HIV-derived lentiviral vectors or adeno-associated viral vectors, AAV. But we have also adeno vector. When we are dealing with the construction of a viral vector, we have to consider, here is the parental, the normal viral genome. So you have he's flanked by 2 terminal sequences, so inverted terminal repeat or long terminal repeat, with a part dedicated to the replication. So here you have gene who encode for protein, or for protein who allow the replication of the virus. Here you have gene to encode for protein, allowing the virus to establish his structure, his 3-dimensional structure, and a part of the gene encoding for the pathogenicity to allow the virus to be pathogen. So we have, when the viral vector is constructed, we have to remove the pathogenic part of the virus. Okay. So usually most of the vector comprise a packaging construct with the replication gene allowing replication and gene allowing the development of the variant structure, and the transgene containing the gene that has to be inserted in the the targeted host cell, and also flanked with the terminal sequences. Then these two constructs, the packaging construct and the viral vector construct, are inserted in the host cell, who is going to produce the recombinant viral vectors. So we call recombinant what is all the products produced by engineered genetically. Okay, so that's it. So when you understood, this is really the basis of the basis of the construction of viral vectors. So that could be 2 constructs, sometimes 3, but we will see it. We'll see that later. So the commonly used gene therapy vector are most of the lentivirus, adenovirus, and adeno-associated virus. They differ by their size. Both of them are, the target cell are dividing or non-dividing cells. I will explain later why. Some of them lead to a chromosomal integration, but sometimes not. Adenovirus suffer from immunogenicity. That means that it generates unwanted immune response. So that leads to which would induce some pathological symptoms. And murine retrovirus is not so much used now. So if I just remind briefly what is the structure of those viruses. First, the retrovirus is around 100 nanometers of diameter, more or less. Is an enveloped RNA virus, which is the important things to know. His genome of about 710 kilobase. He's composed of 2 copies of single-strand RNA genome, and he is able to integrate into the genome of the host cell. He also bears group-specific genes who encode for core and structural proteins of the virus. The core protein are the protein who are complexed with the nucleic acids of the virus, the RNA. And the structural protein are the protein of the capsid around the complex RNA and core proteins. We have also the polymerase, what we call the pol gene, who comprise the gene encoding for the reverse transcriptase. As this virus is an RNA virus, it needs to be reverse transcript to a double-strand viral DNA, protease, and also integrase to help him to integrate the genome of the virus, the host virus, the genome of the host cell, sorry. So how it's, I should show you also his replication cycle. So this virus is able to fuse with the membrane of the cells, and then inside the cells, the viral RNA will be released and reverse transcript to double-strand viral DNA who is able to enter in the nucleus, where he will be integrated in the genome of the host cell, then transcribed into viral mRNA, and then this viral RNA will be translated into proteins, and so taken together, the mRNA and the virus will be assembled to form the virus core structure, and then this virus core structure will be, I would say, budded off by the membrane. That's why he is an enveloped virus, because you have the virus and he's surrounded by the membrane, which is originate from the membrane, which is correspond to the membrane host cell. And then this phenomenon of budding off allow the release of the entire virus, the envelope virus. So when there are a construct of an engineered retrovirus in the purpose of a gene transfer vector is composed by three constructs: the construct for the transgene, the construct for with the polymerase and the GAG gene, and the control also for the viral glycoprotein of the surfaces. Then, when you can see here, the host cell most of the time is what we call HEK 293 cells, and HEK is for human embryonic kidney cells. And then the virus is entering on the cell via fusion membrane release of the nucleic acid and reverse transcription and integration in the genome of the cells, and then production of the protein of interest by the protein, the cell's host cell machinery. Now the adenovirus, his genome is around between 20 and 45 kilobase. He's composed by a nucleocapsid that we are seeing here. It's a double-strand genome. It's a DNA virus non-enveloped, and here is double-strand. His capsid is composed of exon protein that you can see here, and also penton-based protein located at the vertex of the capsid here, and also what we call fiber protein, the spike, that allow the binding of the host receptor here. And we have also minor capsid protein to stabilize this entire structure. And so when the virus, how the virus enters in the cell is recognized by receptor at the cell surface, most of the time glycosylated receptors, is integrated in the cell. He's used the cell's machinery to be transcribed and on mRNA, and so he's replicate. He's transcribed in mRNA and translated in protein, and then all the component of nucleic acid and the protein allow the virus to assemble and then released by the cell after the cell lysis. Next slide. What is the advantage of this adenovirus vector? The biology of this virus is really well understood. The adenovirus have a big genome able to accommodate with large transgene cassettes. So when the gene has a higher gene to be transferred has a large size, that could be useful to employ adenovirus. The recombinant virus can be generated with high titer and purity, which could be important for the scale-up of a recombinant viral vector for future therapeutic use. Something to consider. It's easy to manipulate. As I said, the transgene expression from adenovirus is rapid and robust. He also is able to infect a wide range of dividing and non-dividing cells. And also, he do not integrate into host genome. So he stays outside and forms an episome. The drawbacks is that he's able to elicit immune response, T-cell mediated response, and humoral response with high production of antibody directed against the virus and the host. So which lead to the killing of the adenovirus transfected cells, and also leading to an immunogenicity phenomenon that induce several adverse immune effects, undesired effect for the patient. So that's why it's not the use now of adenovirus vector is discussed in the community. So that's why the people became interested in adeno-associated virus, who have been isolated, I think, first in 1965. And, but it's a smaller, the nucleic acid of this virus is smaller, it's 4.7 kilobase. It's a single-strand DNA. He exhibits a broad tissue tropism. He has several serotypes with different tissue tropism, which could be very useful if you want to produce, for instance, viral vector who go for the liver, or a viral vector able to go to the pancreas or kidney or whatever. That's very useful. He's also easy to engineer, and the capsid has been extensively engineered. As I just said, so he has also is very useful because his capsid can define the virus tropism, and like this you can choose the organ, the targeted organ. And also he's less immunogenic and his exhibit is not pathogen. So that's why it's very important. It's very useful. So this is why he's now is emerged as the preferred choice in clinical and FDA approved application. Sorry. So here is that's the wild type adeno-associated virus, and here is the capsid, as you can see here, with the transgene and the promoted announcer. It has also, I didn't show, but I will show an example later. It has also a packaging construct and also a ad helper to help him to be produced by the host cell. As I can skip this and here. So just here you have a summary of the historical development of adeno-associated virus. In 1961, this adeno-associated virus was discovered. It has been possible to package successfully recombinant adeno-associated virus in 1989. They also developed modification of this virus to rendering able to be persistent to be persistent in the cell. The first application for human was in 1995, and the first clinical trial has been validated in 2008. It was to develop a treatment of the Leber congenital amaurosis. So it's a disease who causes blindness to very young children. And this clinical validation led to the first treatment approved by the FDA, which is called Luxturna, to treat this disease, Leber congenital amaurosis disease. In Europe, the first EMA approval treatment was Libera, and it was developed to treat lipid proteinase deficits, and it works quite well, but the problem is it's very, very expensive, so leading to his withdrawal from the market in 2017. Here you have the development. Here you have an example of a recombinant adeno-associated virus with a packaging construct with the gene comprising the gene responsible of its replication and the gene responsible of his structure. You have also the transgene and what we call the inverted terminal repeat. And how it's work? So he is recognized by a glycosylated receptor at the surface of the membrane cells, and by an cytosis mechanism, he enters into the cell thanks to an endosome encapsulation and travel inside the cell until the Golgi apparatus. Then, inside the Golgi apparatus, you have the acidification induce a conformal modification of the protein of the capsid, leading to the exposition of a phospholipase A2. And this phospholipase A2 disrupts this membrane surrounding the recombinant viral vectors, allowing its release into the cytosol. Inside the cytosol, it can be destroyed through an ubiquitination process, so destroyed by a proteasome through ubiquitination process. Otherwise, it can enter inside the nucleus and will accumulate in a structure without any members but called a nucleolus. And then he will accumulate there in this nucleolus. And then the single strand viral DNA will be released. A second strand of the DNA will be synthesized. And this structure of the inverted terminal repeat allow the interaction between intramolecular interaction of inside the DNA or intermolecular interaction, and that's why you have this cycle form. But it could be an episomal, a unique cycle, but it could be also dimer, or what we call a circular concatenaire. And then this DNA will be transcribed in mRNA, and we obtain, and after that, and the next step will be the protein production. Okay. So the next step is the recombinant adeno-associated virus engineering. It could be engineered quite easily through his capsid, for instance, as we know that several serotypes could be obtained, and will condition the fate, the in vivo fate of this viral vector in the organism. Different components of the genome could be also engineered. The inverted terminal repeat. The promoter could be optimized. We have also riboswitch who can regulate at the level of the post-transcription level. There are non-coding metabolites that could riboswitch are non-coding mRNA that could regulate metabolite as well as the gene expression. And also a post-translational regulation can be also occur through addition of different type of molecules. And also this post-translational regulation can be performed by the control of the alternative splicing process. So, as I said, you have different serotypes of the adeno-associated virus, and that have an influence of their in vivo fate and their tissue tropism. As you can see here, you can see the different tropism of the different adeno-associated virus, and you have the modification that could be bring to allow them to target more selectively one organ. So you can also, so it's exactly the same. It's just about the serotype of the AAV vector and a summary of their tissue tropism in humans. Sorry. So, but we have also to say that it's important to note that we have anyway immunological barrier that could challenge, we say, that could be detrimental to the successful AAV, recombinant adeno-associated virus gene delivery. And you have, for instance, production of antibody directed against the viral vector. You have also activation of immunity via the toll-like receptors. You have also, as I said, through the ubiquitination process, degradation by the proteasome. There is also some antibody who are able as well to recognize the transgene here. So you have many things that also can be detrimental to this transfection. Here is all the current approach that could be followed to manufacture recombinant adeno-associated virus. The most widely employed is this one. So as I said, you have three constructs: the transgene, the packaging construct, and what we call the ad helper, who can help the transfection of the virus inside the host cell, mainly HEQ293, but you can also use the HeLa cells or A549. You have also as a way to produce this, to manufacture this recombinant viral vector. You can use baculovirus insect cells, which is another line, another virus for, and they are produced in insect. I will present it in another lecture about production protein, this system of expression. You have also so you also by using recombinant herpes simplex virus and also this other method as well. So you have many methods, but the most widely used is this one, the transfected base one. Otherwise, it's other system. Here is to show the clinical application of the recombinant adeno-associated virus and in different human disease. You have here a spectrum of various diseases. It's related to, so it's some of them are approved, some of them are related to ongoing clinical trials. So you have neurological disease, ocular disease, cardiovascular disease, cancer, hematology disease, metabolic, and neuromuscular. So you have many diseases that are under clinical trial. And here is all the example of approved gene therapy. So the virus vector has been used for a long time, and they are employed for many years. So it's more well mastered by the researchers, let's say. Different viruses can target different types of cells or tissue. Adenovirus and adeno-associated virus represent more than 80% of approved viral-based gene therapy projects. So you have I think it's a result of last year, 40 ex vivo gene therapy have been approved, 21 in vivo gene therapy are approved by US FDA administration, and 29 therapy use viral vector for 6 therapies who use non-viral vectors. So just as a quick view of the manufacturing workflow of a viral vector, it's one is IV. So you have an upstream process with a scale-up, and then after the purification is the downstream process, and at the end is the formulation, what we call fill and finish. So first, the production of the plasmid, the cell expression, the plasmid transfection in the cell, and the viral vector production. So that is on the upstream process. And then after the purification is the downstream, and the formulation is the last step. Here I present the non-viral delivery tool. So that's a physical method, but we go quite fast. So you have, for instance, microinjection, needle injection. So it's a direct injection in the target site. You have also what we call gene gun electroporation or stone operation. You have ultrasound, acoustic or electric current who is applied, allowing the formation of the pore, which allow the nucleic acid to enter inside the cells. You have also what they call magnetoporation. The genes are located in magnetic nanoparticles, and then the magnetic nanoparticles are guided inside the cells thanks to the application of magnetic fields. So as you have seen, viral vector remains for the moment the dominant choice for the indication requiring long-time expression or lasting correction, thanks to their tropism and their in vivo efficacy. You have a non-viral vector experience a growing interest for the researchers, so probably is the future. And now in the clinical practice, several approved drugs, as I said, are already based on non-viral systems. And numerous clinical trials are evaluating the interest of lipid nanoparticles or polymers. You have also the field of what we call the genome editing, such as CRISPR-Cas9, which is composed by RNA and coupled to an enzyme. So the RNA allow the precise targeting of the gene that has to be edited, and the Cas9 allow the cut the gene and allow the replacement by a donor DNA. Here is the list of the FDA and EMA approved adeno-associated vector-based therapy. So you have the Luxturna, you have several. The indication is liver congenital amaurosis, spinal muscular atrophy, hemophilia A and hemophilia B. So to administer gene therapy, as I said, you can perform systemic injection that's suitable to treat hematological disease. So in this case, it's what they call the cells is modified genetically, which is the case of the CAR-T therapy. I will show you example with CAR-T therapy after that. And they often require high dose but may cause off-target effect. That's the risk, and potentially triggering severe immune reaction. And you have local injection, which is a method for relatively isolated organs. So you have that's the case, for example, for the eye. So you can administer directly the recombinant viral vector in the eyes or inner ears or brain. Sometimes you can reduce the required dose of gene therapy product and reduce the severe risk of immune response and avoid massive administration of invasive administration and risk of uneven distribution because you administer it locally. So the first, that's the historical development of gene therapy. So the first gene therapy approved was Gendicin. It was in China, and this was to treat cancer of head and neck related to squamous cancer cells. In this case, it's adenovirus. I cause here this color, the code here for the color. So it's an adenovirus, and he was injected directly intrathecally to the person, and he really lead to a significant improvement of the disease, but associated with a classical chemotherapy. I already present Glibera, which is a lipoprotein lipase deficiency. I will explain the treatment of Leber congenital amaurosis, and treated by Luxturna. Here is the first treatment of the first CAR T cell to treat leukemia. You have also a new one, for instance, Calsody, which is an antisense nucleotide to treat one form of amyotrophic lateral sclerosis, the one who exhibit a mutation of a gene called SOD1, which induces the production of a protein exhibiting cytotoxicity. And so here is to silence, so the idea is with the antisense is to render this gene silent. So that's an ongoing trial. So 2 examples. So first, Leber's congenital amaurosis, and the next one will be the CAR T cell. So Leber congenital amaurosis causes visual impairment or blindness within the first year of the life. That concern between 1 to 30 or 50,000 births, for 1 in 30 or 50,000 births. The clinical feature is for this child severe decrease of the visual acuity, blindness, and this is caused by mutation in gene encoding for retinal protein, who are listed here, and the gene therapy concerns this protein. It's called RPE65. There is no curative treatment prior to gene therapy. And how it works? So here we have it's an adeno-associated virus. So you have the 3 components: the transgene, the packaging construct, and the helper. And they are transfected into the cell, so the HEQ cell, and then the harvest is purified, and we obtain this transgene here, inserted in the recombinant adeno-associated virus. So here is the dose of the genome. Sorry, it's in French, but it's 1.5 11 to 10 recombinant virus, who is injected in each eye. And it's 1 injection in each eye with at least 6 days between the two injections, with an immunomodulatory treatment such as prednisone before and after the surgery. Why only 1 injection? Because the retinal pigment epithelium cells stop dividing after 1 year. So the DNA will persist in the episomal form inside the cells. So you can see here the enter of the vector by endocytosis and the release of this vector in the nucleus and the episomal form and the production of the protein RPE65, who is mutated in the case of this disease. And the new protein will enable the restoration of the visual cycle. Sorry. The next example is the chimeric antigen receptor. So that's a mixed cell therapy and gene therapy, because you have mutation. It's a mutated gene within. It's a cell with genetically modified, and will be used to treat some form of leukemia, and often leading to a long-term remission in refractory or relapse disease. That's why it's important. So it's considered as a combined advanced therapy medicinal product. How it's work? So you have a T cell engineered with a chimeric antigen receptor, so-called CAR, and you have here, it's composed by a part of the Fab fragment of the antibody. So the fragment involved in the recognition of the biological target in an antibody, they is associated with the co-stimulation molecules and to form these chimeric antigen receptors. So I will, in the next slide, you will see, you will have a better idea of this chimeric antigen receptors, T cells. So you recognize here the part involved in the recognition of the biological target. In this case, is a tumor is a tumor cells. He's combined with a single intracellular T cell receptor, which is called the signaling domain CD3. But this CD3 exhibits a short persistence. That's why they add, in the second generation of CAR T cells, a co-stimulatory domain, which called the CD28.41BB. And this, from this second generation have emerged 6 commercially available CAR T cells. In the third generation, they add they combine the two co-stimulatory domains, CD28 and 41BB. The fourth generation, they also allow it's what they call the armor CAR T cells, who will modulate the microenvironment of the tumors and activate further immune cells. So the next generation concerns what we call B-specific CAR T receptor that could link to two types of cells. That's the timeline, just to the rapid timeline, just to say that the first concept of the concept of the CAR T cell was first proposed in 1987, and they suggest that this chimeric receptor can induce the T cell activation against tumor cell. And the first generation of CAR T cell was developed here in 1993, and then the second generation of CAR T cell was in 2002, and the first clinical. So you have 2004, and the first clinical success of CAR T cell therapy was in 2011. So it's quite recent. Here you can find in this table all the approved CAR T cell by the European Medical Agency, EMA, to treat B-cell malignancy and multiple myeloma. So you have listed here all the CAR T cell therapy developed here. How it works? You have to treat the patient. The cell are T cells are collected from the patient. They are modified genetically because it's an autologous process to introduce the CAR gene inside their cells. Then they obtain the CAR T cell from the cell of the patient, and when the CAR T cell obtained, they are administered to the patient to treat his disease. So it's really an autologous. So the patient is treated with his own cells. It's not heterologous. In this example, for instance, you can see here the construct to produce the CAR. So it's the genetic engineering. So you recognize here the part encoding for the fragment of the antibodies, the co-stimulation domain, the intracellular domains leading to the activation of intrasignaling pathway. And these plasmids are inserted in a recombinant retrovirus. And this viral vector is inserted into the cell, and that which lead to the production of the chemoantigen receptor T cell expressed at the surface of the cell, and he is able to recognize specifically the tumoral cell and destroy the tumoral cell. Here is how it's work. So that's an example with the second generation of CAR T cell. So you have the T cell, the signaling, the signaling pathway, and the co-stimulatory domain. And when the linker or the fragment of the antibody recognize the antigen of the tumor cells, that will activate the signaling pathway and will lead to the transcription inside the T cell of effector function, such as interleukin-2, and also the production and the release of two types of protein called perforin and granzyme. The interleukin-2 is able to stimulate the production of other immune cells, which could help the treatment. And the porphyrin is able to form a pore inside the tumor cell, allowing the granzyme to enter into the cell and cause his death. So then that's how the tumor cell is destroyed. Okay. And this is an active. So that's why the CAR T cell is really efficient to treat some form of malignant, some form of leukemia. What is the drawback? The drawback is that most of them fail to display a long-term tumoricidal reactivity because you have exhaustion or apoptosis after activation. And we have also a cytokine release syndrome due to the activity of the CAR T cell inside the cell, which can be also represent an important challenge because it's also that's very dreadful for the patient. So that's for the CAR T cell, and then you have the next the future, but I will present this later in another course. We have alternative platform and emerging genome editing tools, such as the zinc finger nuclease, transcription activator like effector nuclease, which is quite similar to the CRISPR-Cas9 that I have presented already. That's the end of the lecture for the gene therapy. It's true that it's good that I have my. I have prepared. Here is it. I have prepared some questions about the lecture. So just to. Alors, which one? So you are allowed. Pardon, oui. Non, vas-y.
Tu vas arrêter là pour poser des questions.
Non, j'ai préparé un exercice et des questions pour eux.
D'accord.
That's for them. Okay, sorry. It's a question for you. It's you are going to work. You are allowed to use your smartphone here, because that I hope is working. So you have to copy the. I hope it's working. Ouais, vas-y, tu me diras si ça marche. There is only 4 participants for a moment. How many? I have not your name, so if there is a wrong answer, that's not important. I don't know who is. So if Ricardo made a mistake, I don't know.
Je n'ai pas mon prénom.
Voilà. 19, 20, 21, 22, 23. Mais il y a encore des... Is it working? Is it okay? Parce que j'ai 24 participants, mais on est plus. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, 17, 18, 19, 20, 21, 22, 25, 26, 27, 28, 29, 30, 31. Ouais.
Puede conectarse a internet, perfeccionamiento docente, clave UDEC 2020.
Okay. So I see. Everybody is connected? Okay. Is that right? So, the first question is not a difficult question. Gene therapy is best defined as destroying origin in cell, introduce. You can read yourself. Je devrais cacher peut-être. On voit ce que les gens. Attends. Attends, comment je fais pour... Ah mince, sorry. Ah, attends, ça répond. Attends, ah oui. Hop, like this. Ah. Hein, ouais.
D'ailleurs, je ne sais pas si tu peux masquer les réponses parce que du coup, c'est vrai qu'on va.
Oui, ben je sais pas, j'ai essayé de voir si je peux. Ouais, je peux faire comme ça. Ouais. Et ça le cache. Oui, mais je peux faire comme ça. Ouais. Parce que sinon, oui, ça influence, oui. Oui, tu veux.
J'ai répondu toi.
Ah, pero ¿y la pregunta? ¿Para que se vea la pregunta?
¿Sale en el teléfono?
Ah, ya. Dice, control P, elementos.
Oui. C'est bon, je paye. Alors, correct answer, this one. Merci. 100%. Which of the following is the most commonly used as vector in gene therapy? Ouais, ce qu'il y a, c'est que ça cache. Voilà. Ah, c'est bon. Ok. Oui, I wait a little bit. 28, ok. Je peux te passer mes transparents, toi, tu vois. Okay, maybe I can. I think everybody knows the answer. Ah. 90%, quite good. Next question. Yep. Which viral vector integrates its genetic material into the host genome. Attends, hop. Adénovirus, rétrovirus. Ah, là, c'est que tu n'as pas écouté. C'est pas grave.
Tu vas pas montrer notre résultat, non?
Non, 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 je sais. I didn't. D'accord. Je peux y aller?
Oui.
Rétrovirus. Ah.
Il y a des gens qui n'ont pas suivi.
So maybe it's me. I haven't explained very well because the answer was retrovirus. For adenovirus and adeno-associated virus, it's an episome, remember? So, ok. Hop, attends, je cache. Hop. Which vector is considered relatively safe and widely used in clinical trials due to its lack of pathogenicity? Sorry, there's a fault. Eh ben, ça montre. That's useful to know what is understood, what is well understood and what is not well understood.
Moi, je utilise les réponses.
Oui, mais tu es tout seul. Tu es tout seul alors.
Without IA. Sin inteligencia artificial.
Moi, il faut que j'utilise l'intelligence humaine, mais
Alors, en général, c'est personne, ok. Ah, it will be better. So the recombinant adeno-associated virus is non-pathogenic. Voilà.
J'aurais dû capter.
What is the main limitation of AAV vectors? I did not insist so much at this point. So if you don't know, it's not. I can understand. Correct answer. Okay, great. It's a small packaging capacity. Ok. Alors, hop. So, l'antiviral vectors are derived from which virus? Influenza, HIV, Epstein-Barr, or hepatitis B. T'as vraiment rien écouté.
Mais sinon, je te pose des questions sur les opérations. T'étais pas là hier.
Hein?
T'étais pas là pendant mon cours hier.
Non.
Je te posais des questions sur les
Ah oui, voilà, oui. Ouais, je ne me suis pas avancée beaucoup, hein, sur l'ultrason. Mais cet après-midi, je reste en cours. Combien? So the correct answer is HIV, which is a retrovirus belonging to the family of lentivirus. Great. Alors, next one. Ah, zut. Voilà. Why are viral vectors modified before use in gene therapy? La première proposition, tu peux l'enlever. La première proposition peut être enlevée. Tu ne veux pas augmenter leur pathogénicité. The correct answer is, of course, great, to remove their ability to replicate and to cause disease. Of course, you don't want to increase their pathogenicity, you don't want to decrease the gene delivery deficiency, and you don't want to make them visible to the immune system. So, and of course, you want to remove their ability to cause disease. So, great. Alors, Hélène. Alors, hop, 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 hop. What does CAR stand in CAR T-cell therapy? The correct answer is I don't know, sometimes chimeric antigen receptors. CAR T-cells are primarily derived from B lymphocytes, natural killer cells, T lymphocytes, or stem cells. So the correct answer, of course, is T lymphocytes. Good. Next, it's not almost finished. What is the main function of CAR T cell? Produce antibody, directly kill cancer cells, stimulate red blood production, or suppress immune cells? Ouais, mais comme moi, ça me permet de voir les notions qui passent ou qui passent moins bien. Ça me permet de voir ce qui est mieux retenu ou ce qui est moins compris. En fait, quand je fais ça, j'aime bien. Oh, il y en a qui sont pas.
Oui, c'est pas mal. Les cours, les médecins étaient un peu plus.
Ah, peut-être, oui.
Bah, après, ils ont les.
Oui, ils ont les trucs là.
Ils ont les meilleurs yeux.
Non, c'est pas une excuse pour pas bien répondre. Oui, okay, so of course, directly kill cancer cells. So it's the last question. What is the role of the co-stimulatory domain as on CD28 or 41BB in the CAR design? Ça permet de discriminer ceux qui ont écouté, ceux qui n'ont pas écouté. Si tu as dit, anything. Rien écouté. Comment on dit, no escucha? Comment c'est ça? No escucha? Ah, je lui fais dormir.
El mejor puntaje tiene décimas en esa etapa. La evaluación final del curso. No, la profesora.
So correct answer, it's enhanced T cell activation and persistence. Okay, so I think it's it was the last one. So just to come back, just to the lecture, a few, what was the more difficult. So retrovirus integrate into the genome of the cell genome. So it's a virus who integrate the genome. The recombinant, the retrovirus viral vector integrate into the genome of the host cell. All right? And for the AAV, here, adenovirus or associated adenovirus did not integrate into the genome of the cell and form episomal DNA or circular dimer or circular concatemer. But it's not this virus, the genome of the virus, the nucleic acid of the virus did not integrate the genome of the host cell. Okay? Qu'est-ce qu'il y avait dans les CAR T-cells aussi? And if we go to the CAR T-cells, let us here. Okay, so of course, to increase the persistence, they add a co-stimulatory domain. Et c'était ça, je crois que les trucs. So that was the main point. Here as well. No, it's, voilà. Ah oui, parce que c'est pas. Ok. Here. And here the co-stimulation and the activation of synaptic cascade and the co-stimulation of the synaptic pathway induce the proliferation, an increase of the release of interleukin-2, who stimulate the proliferation of other immune cells, but also lead to the production of perforin and granzyme, and the perforin form a pore in the cancer cells, and then the granzyme will go through the pore inside the cell to kill it. And so the CAR T cell is the chimeric antigen receptor will bind with is conceived to bind selectively and directly the tumor antigen of the tumor cells. Okay. So that's it for this part. Do you have any question? No, it's okay. Okay. So we can move to the second part. All right. Okay. Hein? Il faut que je désactive. J'aurais demandé. Celui-là, non. No. No questions for this one. It will be for the next. Ça sera pour la prochaine fois, la prochaine séance. So, is it okay for gene therapy, the gene therapy part? No question? It was clear for you? Okay. Preguntano. Okay. So cell therapy. So this involves the administration of autologous, so it's also called advanced medical. It's considered as advanced medical new therapies, and it involves the administration of autologous or allogenic human cells to prevent, treat, or alleviate disease. You can use the cells to repair damaged tissue or modified cells to deliver missing molecules to the tissues. The cells who are used in cell therapies, you have different types of cells who are used. Stem cells, progenitors, or differentiated cells. So the stem cells have several interesting properties. They can be what we call pluripotent stem cells or multipotent stem cells. So when we say multipotent, that means that they can differentiate into germ-line layer, namely ectoderm, endoderm, or mesoderm. I will explain later to explain what is the link between what is ectoderm, endoderm, and mesoderm. Progenitor is between, let's say, between stem cells and differentiated cells. So it's still ongoing differentiation, but not completely differentiated. And you have at the end differentiated cells. I start with the stem cells. What is important, they bear two essential biological properties. They are able to divide without any differentiation, resulting in the formation of an identical stem cells to maintain a stem cell pool, so they are able to self-renewal. But they also can differentiate, and they can be divided and give rise to a cell committed to a different accession pathway. The stem cell can be embryonic or somatic. When they are embryonic, for instance, so here you have the egg and the sperm, the first stage of the development, of the embryonic development is the formation of the zygote, and the cells obtained are totipotent, and they can differentiate in all embryonic and extraembryonic cell types. Then you obtain the pluripotent stem cells in the blastocysts, and they can differentiate, as I already said, into three germ cell types, ectoderm, mesoderm, and endoderm, and I just keep this to show what is endoderm, mesoderm, and ectoderm. Endoderm layer become digestive system, liver, pancreas, and lung. Mesoderm becomes circulatory system, lungs, skeletal system, and muscular system. And ectoderm became hair, nails, skin, and nervous system. So that's just you to know what is it standing for. So here is the pluripotent cells. And then from the adult, you can obtain somatic stem cells. For instance, you can find them in the bone marrow or on adipocyte as well. And you have two types of stem cells, multipotent cells, who can differentiate into closely related cells, such as cells in a particular organs. Oligopotent cells, who can differentiate in a restricted closely relatively group, such as hematopoietic progenitor or cardiac progenitor. And unipotent cell who has the property to self-renewal, but can only give cells of their own phenotypes. So for example, cardiomyocyte or muscle stem cells. So I can skip this. So the origin and the characteristic is nearly the same thing, but presented in a different way. So you have the stem cell from adult tissues. You have mesenchymal stem cells, which is also an intermediate. You can obtain them from stromal or connective tissues, such as bone marrow, adipose, or umbilical cord tissue as well. You have also the cord blood diversified tissue, embryonic stem cells, and the induced pluripotent stem cells, which is an adult cell who have been reprogramming through from somatic to a stem cell. I will explain later anyway. For the cell therapy, you have application in oncology and immunology. You have hematopoietic cell stem are widely used for cell transplants. Immunotherapy as well to target specific tumor cells. Also, you have a growing interest into regenerative medicine to replace defective cell or repair damaged tissue. That can be, we have a clinical trial for, in the field of ischemic disease after, for instance, a heart attack or stroke. Also ongoing trials on to treat neurodegenerative disease such as Parkinson and Alzheimer, autoimmune disease from diabetes or lupus, and as well as malignant blood disorder. So here is the different indication we can find here as indications such as malignant tumor, genetic disease, solid organ transplantation, for instance, or autoimmune disease. So if I start to the first indication, so for instance, for the hematopoietic stem cell transplant, so the objective is to replace or restore the patient hematopoiesis, which is damaged in case of malignant hematologic disorder, such as immunoglobulopathy, bone marrow failure, immune deficit. So the stem cells are injected intravenously, and they flowed until the bone marrow, and then they migrate inside the bone marrow and relocate and are able to graft. The problem is that, so what is the sources of these hematopoietic stem cells is, yeah, problem, sorry, yes. That could be autograft or allograft, so that means autologs and autologous and heterologous. So it's something strange in here. And they can, so you can see that could be, the cell could be originated by the donor itself and then administered to the donor to treat his hematopoietic disease, Otherwise, that could be allograft, for instance, for blood cordon or umbilical blood cordon or jelly wharton. Here you have the two systems here presented, the autologous stem cell transplant or the heterologous one. So the autologous, of course, is the patient receives a pretreatment for the human stem cell issued from his own bone marrow, and it's administered into his blood. So the stem cell need to be treated, prepared, and it's quite very tricky steps to separate the stem cells and from the other cells, and then to store. And the storage also is something very complicated, and I will show you later in another course that the quality control in this step is very crucial. Then the cells are after they have been stored, they are sewed and then infused into the patient. So that's the different step for the autologous stem cell transplant. But you have also heterologous stem cell transplant. So the cells are harvested from the donor's bone marrows, but he need to be compatible. They are processed and concentrated, and then infused to the patient after receiving a higher dose of chemotherapy or radiation therapies. The problem here for this is that the patient can suffer for what we call the graft versus host disease, or graft versus tumor effect. And in this case, that could the problem is that that could lead to the. Here you can see that could lead to a damaged tissue, because the host with the patient, the immune system of the patient will be activated and could attack the host tissue, but also the tumor, but also the tissue. That could be sometimes beneficial, but that could be also a problem that could be detrimental for the different organs involved, for instance, in acute graft versus host disease. So they could have an effect on the skin, on gastrointestinal tract, liver, or hematopoietic system. So that's really a physiopathology that could happen, unfortunately, quite often. So that's why many efforts have been put to try to reverse this feature. So here you have the mesenchymal stromal cells here who have been widely used, who gain a lot of interest to treat this disease of graft versus host. These are multipotent cells and are found on various tissues of the body. So it's quite an important field of the research in cell therapy, and they are widely used in regenerative medicine as well as immunotherapy, because they are of their ability to differentiate and modulate immune response. So you can see here the source of the mesenchymal stromal cells here. So from bone marrow, adipose tissue, dental tissue, umbilical cord or wharton jelly, or placenta amniotic fluid tissue. Here the mesenchymal cell, and they can differentiate in different types of chondrocyte, for instance, osteocyte, adipocyte, as well as lymphocytes. And if I maybe put it later, what is just to remind you what is multipotent cells, just come back, because it's a new something new. Multipotent cells, just to remind, they are able to differentiate in closely related cells, such as cell in a particular organ. So typical adult and tissue stem cells. Okay. So they are multipotent, and they have critical function, and they also, what is important, that they can differentiate in the multidirectional, in different directions, such as chondrocyte, osteocyte, or adipocyte, as well as allogenic, as I said already. And they demonstrate that they can enhance hematopoietic stem cell engraftment and mitigate the graft versus host disease. Yep, no, just a check. So, as I said, they are used. So they have been they are promising in the prevention or treatment of graft versus host disease and the treatment of autoimmune disease such as multiple sclerosis, lupus erythematosus, systemic sclerosis, as well as diabetes of type 1. Here you can see all the immunomodulatory mechanism of the mesenchymal stem cells. They can mediate through 3 primary mechanisms: direct cell-to-cell contact, also metabolic they can also secrete soluble factors, such here. You can see here, such as all the which can promote or inhibit different metabolic, different immune response. So they can stimulate interleukin 10, interleukin 6, or whatever. But they also can block interleukin 10, for instance, or interleukin 6, depending of the cell, in fact. So they have many modulatory response that could be very useful in the case of the graft versus host disease. So first, when we talk about what I said, cell-to-cell contact, you have the different, they include different molecules such as N-cadherin, as you see, Notch, SFE, and VCAM, and which facilitate adhesion and also deliver essential and quiescent signal for the human hematopoietic stem cells. Here they also can secrete multiple trophic factors, as you can see here, such as vascular endothelial growth factor, SDF, SCF, or OPN. All these factors, trophic factors, are very important to stimulate it also the hematopoietic stem cell engraftments. They can also inhibit the apoptosis mechanism, but they also are responsible of angiogenesis, so which could help also to maintain the endothelial the cells engrafted in a good state. So there are many ways to maintain, to stimulate the hematopoietic stem cell engraftments. So here is, as I said, I forgot the time. So here is the cell-cell contact pathway. So like this, you can. So the mesenchymatic stem cell could interact directly with the hematopoietic stem cells. You have here the multiple trophic factors secreted to also stimulate the hematopoietic stem cells, and they also are able to stimulate the extracellular matrix here, and also stimulate, as I said, the angiogenesis, which help to maintain the hematopoietic cell engraftment. here is all the application of the. In this table, we have you can find a summary of all the application of the mesenchymal stem cell to prevent grafting versus host disease. And here you can find all the sources of mesenchymal stem cells, bone marrow, cord blood, for instance, the disease treated, the doses. You can see that it's quite a high concentration of cells. So you can 10 to 5, for instance, here, 10 to 5 cells per kilogram of the time between. And here, what is the outcome of the result of the clinical trials? So we have here. We can see all the clinical trial involving mesenchymal stem cell, and to prevent, to cure the graft versus host disease. You have a lot of trials take place in Asia, but also most of them is in America. Only one in Brazil. Few are located in Europe. So you can see that you have not so many clinical trials, but some of them, but not so much. And when the study, how to say, to summarize all the clinical trials, we know that it seems that the results could be controversial. For instance, a first clinical trial demonstrated that the cultured human mesenchymal cell was superior to placebo, was not superior to placebo in grafted versus host disease on adults. So that was the first trial who demonstrated that it was not so. The result was not. There is no significant results for the adult. So they can't prevent this. The rejection of the graft from the host. However, in other group of patients, they confirm that the mesenchymal stem cells were more effective than placebo for pediatric patients. And it was in Japan, and here they also show in Canada and in New Zealand that the type of stem cells was able to treat pediatric versus host disease. And in Canada, this Proximal, which is the treatment of using mesenchymal stem cell, lead to the approval of this treatment for pediatric versus host disease. And in Japan, they also another trial showed that those mesenchymal stem cells were effective to treat those patients. So they tried to explain why there was the different result issued from all those clinical trials. It seems that it could depend from many things. The donor, for instance, they exhibit different gene expression inside the mesenchymal stem cells. The proliferation properties are different. The stage of differentiation is not exactly the same. And the colony-forming unique capacity was not exactly the same. That's for the donor. The sources are mainly also. So that's why. So there is that could be related to the donor of this type of cells. You have also the importance of the sources of mesenchymal stem cells. They can be issued from the bone marrow, from the umbilical cordons, from adipocytes, from placenta, for Wharton jelly, so fetal liver. So you have really different sources, and some of them share common characteristics, but some of them display difference in terms of phenotypes and functioning. I don't know if I explained what is Wharton jelly. Just to find up. I think I've put it. Yeah. Sorry, I put somewhere. Ah no. So, but I think I have it somewhere. Sorry, I'm just looking for my for a slide. To show, I think I have it. Oh, it's on another. Sorry. C'est pas là. Non. I know. Sorry, I just found it in another slide, just to show you what is it. Sorry, I need to up. Just. I think it's here. No, sorry, I didn't. But no, Wharton jelly is found in the. Sorry, let's come back to my slide. No. I can't find it, but it's something we find in the. Come back here. Wharton jelly is found on the in the umbilical cordon as well. So different. So the sources of the mesenchymal stem cell could be also have an impact on the treatment. We have also variability in terms of manufacturing. The patient characteristic could vary as well. And also there is a heterogeneity of the disease. Some of them are important, some of them are less important. That could have so the treatment could be more efficient depending of the impact of the severity of the disease, and also depending also of the organ affected by the disease. And there is also something is that the clinical trial design could be different in terms of administration timing, how many times, what is the dosage, what is the administration frequency. So you have many variability which can explain the different results between the clinical trial. So here I can skip because it's the same thing. Figure means the same thing, that the variability of the donor, the variability of the sources, the manufacturing. So that's why we have so in conclusion, there is inconsistent result, even if the mesenchymal stem cells seem promising. There is a high variability in terms of result issued from the clinical trials. So that's why there's still ongoing clinical trial or reflection around this. But it seems that the next they become more and more interested in terms of exosome. I will show you what is. I will give you a few words about exosome at the end of this lecture. So you have many possibilities to explain the inconsistent result of clinical trial, but emerging alternative therapy could be employed. The next step is the progenitor cells. It can be the next type of cells who are used in cell therapy. So a progenitor cells lies between stem cell and a fully specialized stem cell. So it's an intermediate stage, as it is highlighted here. You can see in this part. For instance, you have a pluripotent stem cell embryonic. You have here, it's a cardio-progenitor cell, so just in between the embryonic stem cell and the cardiomyocyte with differentiated. So they are coming from the stem cells. They are partially committed to be a specific cell type, but they have limited capacity to divide, but they still can differentiate into a restricted range of cell types. They are sometimes safer than a stem cell. That's why researchers are interested by this type of progenitor cell, because they lower the risk of uncontrolled growth, which could happen with stem cells, and they are already directed toward a specific tissue. So sometimes you limited the problem of graft versus host, for instance. So they are used for several. They have many indications: blood disease as well, neurological disease by using neural progenitor cells, heart repair with cardiac progenitor cells, and retinal progenitor cells to restore certain eyes. So here I just remain in the figure of the left, where is the cardiac, the progenitor cell, for instance. Here is an example with cardiac cells. Just progenitor cells are here, in fact, in the development. They are considered as unipotent cells that can differentiate only in one type of cells, for instance, epidermal cells, or here, cardiomyocyte cells, for instance. So here I give you here an example of a progenitor cells used to treat heart failure disease. And here, in this case, what they have done, they use human embryonic stem cells, and they treat this embryonic stem cell and force them to derive into cardiovascular progenitor cell. So how they do that? They stimulate the co-expression of a stage-specific embryonic antigen and cardiac transplantation marker to force them to derive from the embryonic stem cells to the cardiovascular progenitor cells. And here, in this case, they used the progenitor and embedded this progenitor in a fibrin patch. So that was this trial was conducted in France. As I will come back later. So that will be, I'll come back later. So here, in this case, what they have done, they use the progenitor cells. They loaded the progenitor cells in a fibrin patch, as you can see here. And then they implanted this patch containing a gel, this patch containing the cells embedded in the fibrin, and they implanted it directly in the myocards here, as you can see in this figure, and in the area where the infarctus occurs. So you know that heart failure is an ischemia of an ischemia zone whose as I said, the surface is 2 centimeters square, 2 square centimeter at the minimum, and which induce a severe arrhythmia causing the heart failure. So here they implanted here directly, locally, in the heart, this patch. And then when they calculate it to check if one way once you have administered and implanted this patch, you have to check that this implantation is successful, and you have to verify that the cell-treated patch are working well. So they monitor the score of the cell, the cells treated with the patch, 1 month, 3 months, 6 months, and 12 months after the surgery, by measuring what they call the left ventricular wall motion score index, and to allow a semi-quantification of the left ventricular ejection fractions. And they showed an improvement, as we can see here, of this score index. Here you can see a timeline of published and of ongoing clinical trial of cell-based and cell product-based on therapy of heart failure. You have many type of therapy, including several ones relying on a cardiac patch. If I come back to the one previously, here you have several examples of cell-based and cell-produced therapy to treat heart failure. So they can use adipose-derived regenerative cells. It's a sort of organoid that can be used to treat to be patched on the ischemic zone, sorry, of the heart. Yeah, right. They can use as well bone marrow cells issue from the bone marrow that can be derived on the cardiomyocytes, and they can use to repair the fibrosis of the heart or the ischemic region of the heart. I will tell you, there is a high field of research relying on immunon pluripotent stem cells, derived cardiomyocytes. So you have somatic cells who have been reprogrammed in induced pluripotent stem cells and differentiate in cardiomyocytes. Here you have the different route of cell therapy for myocardial affection. So that could be, as you just see here, a patch applied directly on the zone where the lesion take place, or it could be also an intramyocardial injection or a transcardial injection. So another field who show a great a new emerging field who show a great interest is induced pluripotent stem cells, which is a very important thing. What we call induced pluripotent stem cell. They can be generated from human, and the cells are reprogrammed and to induce at the pluripotency stage. So that means that you have an adult cell who can come back to his embryonic cells. It's not something natural. This process has been developed by the group of, in 2016, by the group of Yamanaka in Japan. And he obtained the Nobel Prize for this discovery in 2012. And so he's able to, as we can see here, to use, maybe I have a figure somewhere. Here. You can use a somatic cell, and they are now able to reprogram those cells to pluripotent stem cell stage. So that can be used to generate different types of cells, such as heart, neuronal, or liver, and can be used for transplantation or studying disease or testing new drug candidates. So that's enabled the construction of a cellular level disease model and generate a growing interest those last years. That can be used to generate patient-specific cells as well as heterologous cells. But still, you have this type of cell face several challenges. How is it done? So they are able to reprogram this human, for instance, this human fibroblast to be reprogrammed as what we call induced pluripotent stem cells. So for this reason, they have 4 transcription factors are introduced in the fibroblast. The they use a viral vector to carry the expression of to carry this 4 transcription factor in an expression cassette. The vector was viral. It was a lentiviral vectors, but in the first case, in the first publication, but this experiment has been reproduced with non-integrating viral vectors. So with the 2 types of vector, integrating lentiviral and retroviral, non-integrating, if you remember, is adenovirus or adeno-associated virus. They also add in the experiment small molecule to modulate the various signaling pathways. And so here I can skip this. So we can see here the schematic representation of the autologous, the development of pluripotent stem cell for autologous cell therapy. So you have the somatic cell. They are reprogrammed into induced pluripotent stem cell. They also can, when they are back to this early stage of pluripotent stem cell, they can be differentiated and differentiated again. They can be used for many experiments. In this case, it's to produce again a CAR-T cell, and they also and after passing the step of the quality control, they can be administered to the patient. So here, they really use the adult stem cells of the patient. These cells have been reprogramming into pluripotent stem cell lines and then redifferentiate for another purpose. Okay? So it's fibroblasts who became CAR-T cell of the patient. So in this case, it's an autologous cell therapy, but and in the second case, this cell therapy can be allogenic. That means that you use iPS obtained for another patient, and the cell can be and it can be used to be differentiated. And here again, it's in the CAR-T, it's another CAR-T cell, and then transplanted to a different patient. So you have the 2 possibilities. So that's the schema. So these two examples are really schematic. It's the general principle who are exposed here. But what is important to understand is really that you have adult cells, somatic cells, that can come back to the early stage of stem cell and gain pluripotent properties. If I come back to the beginning, just remind what is the pluripotency as this. Sorry, I find it. Ah, c'est là. Voilà. Excusez. So just pluripotency. Yep. So that can be different. They can differentiate into germline layers such as ectoderm, endoderm, or mesoderm. So it's the embryonic stem cell stage. And if remember, if I was somewhere, no, c'est là. And just mesoderm, you remember, it's that could be become several things, digestive, liver, or circulatory system, or nervous system, for instance. But this field is still in development. Sorry. Okay, and here is an example of a work who have been. Sorry, I put something strange in the slides. Just a minute. On a fait un truc bizarre. Okay. So they perform here experiments of cardiac organoids made from, derived from induced pluripotent stem cells. So here you can see the two types of, and they compare, sorry, they compared two types of organoids from heart. So the cardiac organoid derived from induced pluripotent stem cell, or a derived cardiomocyte, and heart organoid, who is here, is from normal cells. So they compare the classical cells, organoid issued from classical cells of heart cells, and they compare that with the cardiac organoid derived from human-induced pluripotent stem cells, just to be sure that the two types of cells exhibit the same biological properties. Here in this, what is the fundamental property, biological property of heart cells, mainly cardiomocytes? They are able to beat. I mean, of course, because they are contract and decontract, because it's the role of the heart. So they just, that was the first thing they compare. And they wanted to know if they exhibit the same ability to beat. And we can see that here that the percentage of beating is nearly the same on both organoids. Organoids derived from human-induced pluripotent cells, and organoids derived from normal classical cells. And they show as well here, if the video is working. So here we can see the organoid and with the cells who are able to beat. So, I think. So they also wanted to know if this type of cell can be used as a model to study in deep the impact of ischemia and reperfusion injury on the heart. We know that if we have ischemia, so that that lead to the beginning of the heart failure, could lead to the heart failure at the beginning, the first stage of the heart failure, and then after we can try to reperfuse the heart after this ischemia, and to evaluate the effect of the injury area. And so that's why they evaluate the ability of this organoid to reproduce this kind of effect. So they also as well again compare the cardiac organoids, which are issued from the pluripotent cell and the host and the normal cell, the normal organoid, and they both show that after this ischemia reperfusion, they observe as well again in both cases an overexpression of the hypoxia inducible factor who is overexpressed after ischemia. Okay? You can see here. And so why this factor is overexpressed? Because he's able to activate transcription of many gene, and this is this activation is triggered by this ischemia, and he wants of course to repair the injury triggered by the ischemia. That's why he is overexpressed, and that is a normal sort of normal situation after a stress. Okay. What time is it? I think my clock is.
10h50.
Ah, ok, je l'aurai temps alors. Ok. They also see microscopy perform experimental microscopy to see what the impact of the ischemia on the ischemia process on these two type of organoid, and they can check they can see that there is of course apoptosis on this injured organoid, and it's what allowed us what we can see here, the tunnel assay here. So to finish here, here we can see the clinical trial performed with those type of cells. We can see here, and also this trial can be. So here is the trial. If we are between 2021 and 24, that's the previously identified trial in 2021, and here is the new identified trial in 2024. And here we can see also that all the trial to perform to all the trial perform on the different targeted organs such as brain, heart, eyes, and so on. And we can see here the distribution of the trial per country. So you have an important part of the trial performed in North America, one in Brazil, a few of them in Europe, some of them, a lot of trial also in Korea, and in China, and Japan. So that's the part for the human induced pluripotent cells. Here is other example that concerning the regenerative therapy. So here we can see it's isolate, isolation, and transplantation procedure to treat diabetes. So they use a donor pancreas. This pancreas is submitted to different treatments to isolate isolate cells and to administer these isolate cells to the pancreas of an isolate to a patient who's suffering from diabetes. The last example is the cell engineering technology for wound healing and tissue regeneration. So wound healing is an intricate and biological process that repair injured and damaged tissue. But any irregularity of this cascade of events can contribute to a critical non-healing condition. That's why several treatments, and especially when people are suffering from diabetes or ischemic disorder, the wound healing could be altered. So that's why also there is also a lot of development towards directed targeting cell engineering technology for wood healing and tissue regeneration. And I have here a few examples. So what happened when we have wood healing, the traditional treatment is bandage here, sample covering. But now we have, from 2000, interactive engineering tissue have been developed and to incorporate growth factors or peptides to promote the healing. You have also smart responsive hydrogel, for instance, to release drug on the wood environment. There are also 3D bioimprinting as well to for instance, and then can fabricate skin or tissue construct and also as well cell-based therapy using autolog or engineered system cells. And the role of the cell on the wood healing, you have for instance the fibroblast who is located in the dermal layer of the skin and play an important role on proliferating and remodeling, for instance. They also produce all the extracellular matrix proteins such as fibronectin, collagen, and protein glycan. Also the keratinocyte, who is the primarily cell type in epidermis, and after injury they could undergo phenotypic switch to allow them to proliferate, migrate, and ultimately differentiate to restore the skin barrier. And also, the last, the endothelial cells who are located in the inner lining of the blood vessels. And it's also okay for wound healing. And here is the different cells that could be employed to treat wound healing. So there have been different experiments to use differentiate mesenchymal stem cells. We have also experiments have been performed with IPS and also prevascular 3D cells and to construct an hydrogel scaffold. So the cells are entrapped in a hydrogel scaffold, and fibroblasts and genetically fibroblasts and keratinocyte cell engineering, and they integrate genetically a growth factor expression. And here is the treatment, and then I finish with this example. It's a dermal graft. It's used to seed the human dermal fibroblast onto a polylactin mesh scaffold, and the cells are allowed to expand in this three-dimensional matrix containing collagen and various growth factors. And he has been approved in the USA. And another example is Appligraph, which construct with fibroblast and bovine collagen. And he's able to reactive keratinocyte and correcting growth factor signaling and suppressing the scarring. So that's the other example, which is also approved and commercialized. And the last is the exosome, but tu en as parlé hier, les exosomes. You have talked about exosome, no? Also the exosome also raise a lot of interest, and the exosomes are secreted by cell. And what is interesting with the exosomes is they reflect the physiopathological state of the parent cells, and they have been they raise a growing interest as they can be used for biotherapy as a biomarker of drug nanocarriers, and they have raised a lot of interest to treat for the treatment of the graft versus host disease, and as well with heart disease. So that's it. Okay, and I finished. Okay, j'avais fait pas beaucoup. So, thank you for your attention. If you have any questions.
café, a lo mejor. En el café pueden hacer consultas. Vamos a cortar el café. Pero volvemos a combate reversible.
Ah bah, ah bah.
Bueno, pueden mirar.
Globalement, en fait, ils sont toujours administrés, ces traitements localement.
Souvent, oui, pour notamment quand c'est du régénératif, oui.
Ouais.
Vámonos.
Si j'ai juste de vous parler.
Okay, can you hear me? Yeah? Okay. Yesterday we finished on this idea, okay? So I presented you several applications of nanomedicine. Here are the three main I selected for you to remember at the end of last course. The idea here was that nanocarriers, nanoparticles, they enable some interesting targeting, especially in terms of organ, tissues, selectivity, okay? And we have seen that they not only allow an increase of efficacy, but also a decrease of side effects. Today, we're going to see another type of applications. We are still talking about nanoparticles, delivery, improving delivery, etc. But we will really focus at what's happening at the cellular level. And we will see that there are other challenges to overcome really when it comes to crossing the cell membrane. And that has particular applications for the delivery of genes. And for that, I'm really using what Claire has just shown you in terms of nucleic acid delivery. But I won't talk about viruses. I will talk about how nanoparticles based on purely, excipients, molecules, chemical, can also enable the delivery of nucleic acids without requiring any virus. But before doing that, I need to tell you a little bit about the mechanisms of transport of drugs across the cell membranes. And to do that, I will really make a comparison between what's happening for molecules, here I mean APIs, and what happens for nanoparticles. I think it's really important to make a distinction between both to really understand why we need nanoparticles to achieve gene delivery. I will talk briefly, just a few slides on the molecules and then spend more time on the nanoparticles. If there's just maybe one scheme to remember, that will be, I think, this one. This is a comparison between what's happening for APIs and for nanoparticles. When it comes to APIs, drug molecules, they will interact and enter cells by two main mechanisms. The one we call simple or passive diffusion, and the other, the use of molecular transporters. So here when we say transporters, it means some proteins, molecules that are within the cell membrane and that will ferry the molecules inside the cytoplasm. By the way, the cells we are talking about here can be either cells that you want to target, for example, cancer cells in which you want to deliver some anti-cancer drug, or an epithelial endothelial cells if we talk about crossing a biological barrier for an absorption mechanism, for example. So drug molecules enter those main routes, and drug particles enter by mostly endocytosis, in which case you have the formation of a small vesicle that entraps, surrounds the particles and ferry it throughout the cytoplasm. And actually it's very separated. It's really important to understand that both are separated, and nanoparticles may not enter through those mechanisms. So just to help you make these distinctions, I'll just tell you a few words about the simple diffusion, which really concerns small molecules. Okay, so the smaller the molecules and the more apolar the molecules, the better they will diffuse by passive diffusion. So those kind of molecules are really the ones that can cross. And whenever you have ions or hydrophilic molecules, even if they're small, they may not diffuse through passive diffusion, except of course water, which freely or more or less freely diffuses through the membranes, and that's the origin of osmotic pressure, of course. Then the use of transporters is really important in pharmacy in general. You can have several mechanisms, either through a passive transport, which this is the one we call facilitated diffusion. This is a very interesting mechanism because it really allows small hydrophilic molecules to diffuse using the concentration gradient. Basically you have like a transporter, molecular transporter that has a random state, can be in both states, and by doing this it will allow the equilibration of concentration between the outside and the inside. So it shares some characteristics of the passive diffusion because it doesn't require any energy, it uses the concentration gradient, but it is specific to a group of molecules that may not diffuse naturally throughout the membrane. Then maybe the more common one will be the use of energy, and this is what we call the active transport of drug molecules. And actually what happens in reality is that you may have a combination of these different mechanisms. That's what makes it sometimes a little bit difficult to study in details. And this is what happens naturally, for example, for the absorption of glucose in the epithelium cells. Of the intestines, where you have actually a facilitated diffusion for in one side and an active uptake in the other side. The active uptake to go against the diffusion, the gradient of concentration, and the facilitated diffusion to go in the direction of the gradient of concentration. Those are actually important to understand because even though the nanoparticles can use the binding to the cells, to the cell receptors, they may not be transported directly throughout this type of transporter of molecular transporters. But rather for nanocarriers, we will see that endocytosis is the main route of entry. And endocytosis actually can have very, very different modalities because endocytosis just means for a cell to take something in and with a vesicle. And actually the ports of entry can be divided into two main mechanisms termed phagocytosis and pinocytosis. And well, it's always interesting to note that this comes from the Greek. So this guy speaks Greek, so I should be careful, but phago means to eat, right? For a cell to eat. So phagocytosis has been termed by biologists to describe how cells take big particles. And pinocytosis means to drink, right? So for a cell to drink something, or actually to sample the extracellular medium for solutes, okay, molecules. And if you remember what we said yesterday, actually, when we talk about nanoparticles, we sometimes have molecules, we sometimes have particles, and we also have the intermediate states, okay, some colloids, nanoparticles, more or less soluble, more or less rigid. And it is interesting to note that actually nanoparticles can use all those ports of entry into the cells, and there's not a clear distinction between phago and pinocytosis. However, those ports of entry are different as a function of the type of cells. And for example, phagocytosis is only is restricted to a group of cells that we call phagocyte. For example, macrophages, dendritic cells. And the phagocytosis mechanism occurs always in a similar way. When we are using the intravenous route of administration, there is the opsonization process that occurs in the plasma, which is the adsorption at the surface of the particles of a lot of a range of macromolecules, either some very non-specific ones or some complement protein also. And those adhesion actually triggers the recognition by the phagocytes, and most of the time it's the Kupffer cells. And you see that you have receptors corresponding, for example, to the fragments of the immunoglobulins, to the protein of the complements too. And this adhesion triggers the formation of endocytosis vacuoles by the formation of the polymerization of actin. Those pseudopodia form a phagosome that is then completely ferried inside the macrophage cytoplasm, and you then have the fusion with lysosomes and an acidification of those vesicles. It's interesting, you know, because those actually enzymes, they work only at acidic pH. And this is why they can be used by the cell only in the phagocytes, in the phagosomes, sorry, because then you have the acidification to allow the enzymes here to be active. And this leads to the degradation actually of the particle, because it's a natural mechanism of defense against bacteria, for example. So if you want to do drug delivery, you need really to control the way your polymer will be degraded here, and also to think about how your drug molecule will be able to escape. And we discussed this yesterday, for example, when you are doing some delivery to hepatocytes, well, you need to ensure that your drug will diffuse throughout in these conditions and to be available in the proximity of the phagocytes. Phagocytosis is really used and really studied, quite well understood actually, you know, for many years by electron microscopy, and today we study this mostly by confocal fluorescence microscopy, which is interesting really because it allows you to see, I don't know if you know these techniques, but it really allows you to monitor what's happening inside the cells. And for what we're studying here, it's very important, because if you just look at your cells by fluorescence, you may not know if your fluorescent particles are at the surface of the cells or inside the cells, right? Only fluorescence by confocal, in the confocal technique, can give you this type of information. Then you can make some correlation to understand how well nanoparticles are taken up by phagocytosis. There's been a number of studies as a function of the size, as a function of the type of material, and usually it is understood that the bigger the particles, the more interesting the phagocytosis process occurs, but it can also decrease in terms of number of particles. But actually, we can see a lot of different results in the literature, and it is sometimes difficult to make some strong correlations in terms of the materials especially. However, the surface of the particles, of the nanocarriers, has a strong and well understood influence. In particular, when you have some highly charged surface, that means not only hydrophilic but positively charged or negatively charged. For example, you know, first generation liposomes or lipoplexes, they may have a very important uptake and also opsonization. The same is true for hydrophobic surfaces, and this is the case when you have some hydrophobic polymers such as PLA, PLGA, polystyrene, polyalkyl cyanoacrylates. They also trigger opsonization quite efficiently, and therefore a cell uptake by phagocytosis. What is interesting is that when you're in between those two systems, in terms of chemistry, I mean, this is the case of a hydrophilic surface like pegylated liposomes, pegylated nanoparticles. And you remember yesterday we said this is really the case of the second generation of nanoparticles, which avoid or delay the process of elimination by phagocytosis. So if you have pegylated surface, they are hydrophilic but not highly charged, and especially also in the case of small nanoparticles, well, this is the case where you decrease the opsonization and therefore the phagocytosis. And then if you need, for specific application, you can also increase this phagocytosis by grafting some specific ligands that will promote the uptake by phagocytosis. Then you can also play on other characteristics of your nanoparticles, you know, the shape, the size, so size we discussed, but the shape and also the stiffness And it's pretty fun, actually. Well, several studies have shown that the stiffer the particles, well, the better they are engulfed by nanoparticles. And one explanation may be that they look like something not quite natural for the cells and something foreign. So maybe that's a reason why this stimulates the engulfment. But conversely, actually, or on the contrary, more rigid particles may not be opsonized as efficiently. And this is something that is quite known for liposomes and cholesterol. The more you put cholesterol inside the membrane of liposomes, the more they become rigid. And that actually offers less possibility for opsonin to really find their way and to adapt to the surface. And this is why it may decrease the opsonization. So you see some quite diverging here results for the stiffness. And another parameter that I found really interesting is the shape. And there are more and more studies right now to design some interesting nanoparticles that are not just some spherical homogeneous nanoparticles, but displaying different shapes. And many studies on this, I actually selected this one because it's one of the first. It's, well, nano or slash micro particles. Sorry, I just have some battery issue. Then at some point, I may need. I don't know if you have a USB. C'est USB-C ton truc ou... Pour l'instant, ça va, mais si jamais ça coince, je pourrais te demander. Pour l'instant, ça va. So here there are nano slash micro particles, and they display some interesting stuff. This group has been able to produce some, from this sphere, some ellipsoid, just elongated particles, more or less elongated, and the disks, and sometimes even UFOs. I don't know how they made that, but at some point it seems to work. Ah ouais, c'est cool.
Bon, attends, on va déjà voir si ça marche.
Ouais, si c'est le... Ouais, si c'est bon, ouais, ça marche. So they managed to produce this library of different shapes of particles, and then the goal was to evaluate the phagocytosis of these particles. Basically, they wanted to answer the question: is an elongated particles better suited to the entry into a cell? Is it the case of something more complex? And that was their study. Désolé, je te...
Ça rentre pas, pourtant c'est la bonne...
Il n'est pas arrivé.
Vous pouvez les brancher ça Ça marche pas, celui-là.
Merde, j'aurais dû...
Et t'avais celui-là aussi. Attends, t'as celui-là.
Ah ouais, ça va peut-être suffire, ouais, effectivement.
Ça va? Ça a l'air de... Ouais, ça a l'air d'être bon.
Ok, oui, ça a fait un petit machin.
Vale, vale.
Ok, it works. It works.
Sí, lo encontramos.
Merci beaucoup. So what, I don't know. What's your guess? Do you think what kind of shape do you think is more efficient to enter a cell by phagocytosis? What would you say? The round? Yeah. UFOs? Well, I'm asking this question because I think the first time I wasn't, there, but I think the first time they observed their results, it was quite challenging. So actually, here, look at this. This is the very same time of particles, okay, the elongated one, And you can see that in one case, you can see no phagocytosis at all over more than 30 minutes, which is quite a long time for a cell. And on the contrary, here the same type of particle, the same cells, well, it enters in just a few minutes. So in a few minutes here, sorry, and here nothing over 30 minutes. And even here they say it's just on the top of the cells, but it's not inside the cells. So actually the answer is, well, we don't really know. It seems that there is no correlation between the shape and the phagocytosis. But actually, if you look more closely, you will notice that here this particle meets the cells, if you want, using really the most sharpened face. Okay, whereas here it's really on the most flat side of the particles. And actually, they perform an interesting modeling here, where to model this idea I've just said. They calculate this angle, which is actually the average of the angles between the perpendicular vector of the surface and all the tangent here vectors. Basically, it means that a round particle is 45 degrees and an elongated one meeting with a sharpened face is a small angle. And you can see here that there is a good correlation between this omega angle and the phagocytosis itself, which means that actually phagocytosis is really triggered when you have this needle shape of the particles that is really meeting the cell surface. But be careful, it doesn't mean that the particles enter like a needle directly in the cells. It actually means that this triggers more efficiently the actin polymerization, and this was proven here by the coloration of the actin. So I think that was quite a more fundamental study, but it's a good lesson learned. So that was for the phagocytosis, and then what can we say about the other routes of entry, ports of entry? Well, I will go more rapidly in here because actually it's important to note that there are many different mechanisms. Most of them can happen at the same time on the same cells, and actually it doesn't always a clear-cut answer. However, it's important to note the main ones. The main ones are the clathrin and the caveolé-mediated endocytosis, and all of them are natural ports of entry for nutrients, communication, and this is particularly the case for here the caveolé one, where you have some receptors that are more or less specific for this port of entry. We mentioned LDL yesterday, for example. And this endocytosis actually works in a very regulated way. You have here the membrane curvature that is triggered by the assembly of the trischelia of this protein, which is the clathrin here. And you can see that this symbol looks like a football, ball. And that creates really the curvature and the invagination of the cell membrane, which is cut by another enzyme, dynamin, and that forms a vesicle of surrounding the particle, which is coated by this clathrin coating, okay, which can be then recycled to perform another cycle of endocytosis. On the contrary, caveolé-mediated endocytosis works in a different way, where you have pear-shaped invagination of the membrane coated here by another protein, which is the caveolé. This one is specific for another group of ligands internalized this way, and the formation is a little bit different, and you have here this caveolé protein, which is responsible for this membrane-specific shape. Other can be mentioned, that such as micropinocytosis, which we see more and more now, which is very unspecific and occurring in a slightly different way, mostly for bigger particles. If I look here at some viruses, you can see that for the viruses, well, several viruses can be really specific of one route or the other. But why is it interesting to actually look at this port of entry of nanoparticle? Well, actually, it's important because the fate of the particle will be different, mostly depending on the routes that they use. If we look at the clathrin-mediated and micropinocytosis ports of entry, actually most of the time the particles will be acidified, the vesicles will be acidified and fuse with lysosome. And that is actually quite similar to what's happening for the phagocytosis, which will lead most of the time to the destruction of the internalized material. Again, if you control your polymer, if you have a drug molecule which is, I would say, resistant enough, it may not be a problem. But if you're delivering fragile materials such as genes, nucleic acids in general, that may be challenging. On the other hand, the caveolin-mediated endocytosis has been associated to a more protective internalization way, where you have a direct delivery to caveosomes and not such harsh conditions. However, this comes with other problems, where actually in this case it might be a little bit more difficult to control the drug release. So that's a little bit the main characteristics, and don't forget that, well, because it's biology, it's complicated, so actually you can have some crosstalks and some different outcomes, right? But the main point here is that depending on the type of molecule you want to deliver, it's very, very important to control the fate intracellularly. And that's mostly the case, and that's especially the case for gene delivery. So how do you study this? Actually, so you have different markers that you can use. You can use a lot of imaging technique, either fluorescence-based or sometimes even electron-based. You can also study the different localization of your drug by performing some increasingly aggressive permeabilization of membranes. And when you do this technique, which we call cell fractionation, you can have access to the fraction that are either loosely associated to the membrane or inside the cytosols or inside the endocytosis vesicles. And what are the results? Well, actually, again, drawing some very, I would say, schematic results can be quite different because the outcomes may depend on the type of cells you use, on the type of particles. Sometimes you can see those kind of trends where you have, positive charge that are more associated to the cell membrane, which seems quite easy to understand. And also here, the presence of mucus can really make a difference for the cell delivery. But the more important, I think, aspect will be how we really ensure that the particles we really have inside the endosomes are able to release their content into the cytosol. Is actually two main techniques that we use depending on the type of nanocarriers. And this is what we call the endosomal escape, because you understand that if your drug is fragile, if your drug needs to be delivered in the cytosols, staying in the endosomes is not an option. So how do you escape this? Well, actually, if you are using some lipid-based nanoparticles, such as liposome, lipoplexes, lipid nanoparticles, actually a good way is to induce the fusion of the particles with the endosomal membrane. And that's particularly the case of cationic phospholipids and ionizable phospholipids, which actually will undergo a specific phase transition upon acidification, and that induces the fusion with the lysosome membrane and leads to the release directly in the cytosol of the content. And that's actually a very, very clever mechanism to deliver a nucleic acid directly in the cytosol. Another option that has been considered, especially in the case of polymeric nanoparticles, which in this case are mostly based on polyamines, is what we call the proton sponge effect. It's quite funny, okay? It's proton sponge. It's like, just imagine that your nanocarrier is able to take some protons, okay, and then induces the rupture of the endosomes. How does it work? It's actually an osmotic effect. When you have this type of polymers, they have a lot of amine functions, and upon acidification, actually those amines will take the protons. So actually, there will be a very important and uninterrupted, if you want, influx of proton, because you have many amines to protonate. And at some point, this will create an imbalance of ions and an osmotic stress on the membrane, and that will induce really the disruption of the membrane just by an osmotic effect. And which is why the researchers have coined this term proton sponge effect. So you see, those are two different understandings of the chemistry of the particles that are really a good way to ensure that your nucleic acid is released. However, it should also be noted that this is quite schematic, right? It doesn't mean that 100% of your particle will really follow this pathway. It's more a difference compared to non-modified or to other types of nanocarriers. But we will definitely use these concepts to understand how we can apply this now to perform some gene delivery using this type of particles. So briefly, what type of nucleic acid do we want to deliver? So I will not go too much into the details because I think Claire has covered that, but basically I will not cover here DNA, okay? We don't know how to deliver DNA using particles, right? You can do that by a virus, you can do that if you really induce a disruption of the membrane by physical means, such as electroporation, for example. Or you can deliver a plasmid DNA, okay, inside the cytosol. But really replacing within the nucleus with just a particle, artificial particle, is something quite challenging. However, playing with the messenger RNA here is something we can do. And we have basically two ways of doing this for a therapeutic purpose. The first is to try to block gene expression of an existing messenger RNA present in the cytosol. And this has been done originally by using antisense oligonucleotides in the 90s and early 2000s especially. And this was basically the idea that you can use a small single strain of DNA that is complementary to the messenger RNA that you want to target. And actually, people found that using maybe just a 20-mer complementary sequence was enough to really block the expression of this messenger RNA. Then there's been an improvement in using sRNA, which is a double-stranded RNA that actually has a different molecular mechanism, but also leads to the same blockade of mRNA expression. So the therapeutic applications of that are, I would say, important, especially if your goal is to inhibit the production of a protein that leads to a pathology, let's say an oncogene, for example, and that is a good option. Now there is another option, which is, what if you want to produce an interesting protein for a therapeutic purpose? Then it's more challenging, because here in the case of antisense oligonucleotides and sRNA, you just need 20-mer sequence. Okay, you need to choose it correctly so that it's specific enough, of course, but it's still quite small. It's not a small molecule, but it's not huge. If you want to produce a functional protein, you need to introduce a complete mRNA, messenger RNA, okay, with everything inside, and that can be thousands of bases, okay, and then that's another story. But it's very interesting because that allows you to produce a protein of interest. Interestingly, however, in both cases, the formulation is quite similar. We are using, of course, the anionic nature of those nucleic acids, and well, by the way, I think Claire mentioned, right, but why isn't it possible to deliver this directly? This is because those are fragile molecules. They are prone to degradation by nucleases. This is something you can manage by modifying the bases, by doing a little bit of chemistry. But it's not always enough. And anyway, in all cases, you may not have any uptake of this nucleic acid by your cells. Okay? Remember, we discussed the ports of entry into the cells. Diffusion is something restricted to small molecules, and you don't have any receptors for the entry of nucleic acids. So instability and need for to promote the entry are the main reasons for using nanocarriers. So how do we produce them? We use, again, the fact that they are negatively charged, and we can associate them to cationic polymers to form what we call polyplexes. So here, the formulation principle is quite simple. Okay, you have an ionic, cationic. Okay, that makes what, by the way? You know, it could make just a big, you know, aggregates at the bottom of your Eppendorf. I don't know if you tried that for already. But if you perform the formulation in good conditions, you may have some nanoparticles. I will show you an example in just a minute. And those are the type of cationic polymers which contain, all of them, a lot of amines because they are protonated at neutral pH. And then you can use some cationic lipids, okay, to form lipoplexes or lipid nanoparticles. There's a slight difference between both of them. I will show you that. The first to be used were actually the cationic lipids. When you mean here cationic lipids, it means permanent cationic. For example, quaternary amines. That means they are always protonated, whatever the pH. That's the more efficient, because you can be sure that it's always a protonated state, will always interact with the nucleic acid. The problem with this is that you can have quite a lot of toxicity, and we have mentioned the aggregation, but there are other mechanisms of toxicity too. Ionizable lipids are an improvement over this, because actually those ionizable lipids can be neutral at physiological pH in the plasma, for example, and leads to less toxicity. And however, they become protonated inside the endosomes. And remember, this is really where they have to play the role of promoting the endosomal escape. So ionizable lipids are really a huge improvement in this field. And those actually two ionizable lipids are actually at the core of the patents of Moderna and BioNTech, Pfizer-BioNTech, okay, which you may have heard of, and I will present that in just 2 minutes. The principle, however, is always the same for these ionizable or cationic lipids. You have this hydrophobic anchor to insert that into a phospholipid bilayer, a linker that can be more or less biodegradable, and a polar head which can be either permanently charged or ionizable. In the field, you will see a lot of those different lipids. This is just to show you that there is a huge variability and a huge diversity of this lipid. DOTMA and DOTAP were really the major ones that really enable the formation of lipoplexes, and then there has been a lot of improvement over this. So let me now give you one example of a lipoplex that you can do in the lab, and then an example of lipid nanoparticles to make some mRNA delivery. And I'll show you why we have those different architectures. So first, let's start with a lipoplex. Lipoplex is really what you have when you start with cationic liposomes and you associate that with a nucleic acid. So this is one example of one of our PhD students who has done that in the lab. So basically, the first here step consisted in the formation of liposomes. So you have many options to produce liposomes. This one was by ethanol injection of DOP lipids. So in ethanol that you add into an aqueous phase. This is, by the way, quite easy technique, easy to scale up, And it is also something that now you can do by microfluidic mixing, quite efficient. So by doing this, we have formed some cationic liposomes. And additionally, we've been able to functionalize those liposomes with a hyaluronic acid to perform some specific coating, either for a purpose of prolonged circulation and also for specific targeting. But in terms of lipoplex formulation, what is important is how do you play between those cationic liposomes, and the sRNA. And here, this core step is just a simple mixing, okay? But it's important to respect, to have, to study in which way you make the mixing and how you perform the mixing. And actually, if you really study the ratio between the cationic liposomes and the sRNA, you can, for example, monitor the aggregation, the potential aggregation. You can monitor the size, the zeta potential. And here, for example, you can see the phase, the charge inversion, actually, when you start from a cationic stuff and you end up with a negatively charged stuff. And looking at where you have this decrease and this phase, this charge inversion, is a good indication of the coating of your particle. And in this case, that was an indication of how we coated with a specific HA polymer. You can also look at this under the microscope. And I don't know if you have ever looked at liposomes under a microscope. It's actually very challenging because a liposome is mostly water, right? So how do you look at this under electron microscope? An electron microscope is just full of vacuum. You don't have water. So actually one way to do that is to perform some cryomicroscopy, where you freeze the sample at very high speed and very high pressure, and the water you get is not ice, it is actually water in an amorphous state, and that allows you to have a preservation of the structure and to observe them. Of course, it's very challenging technique, but very, very efficient. And here, this is really very beautiful actually. You can observe liposomes directly, and the thickness here of this membrane is just 7 nanometers, right? That's quite fascinating, I find. So you can also see that, how to say that, producing liposome by ethanol injection does not lead to something very, very homogeneous. You see some oligolamellar here, and you see some different sizes. And interestingly, when you add a little bit of sRNA on these liposomes, you see some very random structures, not very homogenized, not very well organized. But when you put a lot of sRNA, then you get some more regular shape, regular particles. And actually, I hope you can see that, but you can see some very onion-shaped particles with an intracellular, intralamellar space that is very well defined. And those are really a great example of lipoplexes. And we have even been able to monitor actually the location of the sRNA within the lipoplexes, because we found that upon observation of these particles, the electron beam actually leads to the degradation of the nucleic acid. And actually, if you just look at the same field for more than a few seconds, actually, you can see a progressive degradation of the sRNA, and that really is a good actually proof that the sRNA is located inside your lipoplex. So now, how do you ensure that actually the lipoplex can deliver efficiently the sRNA? This has been actually done using what we have called a reporter gene. Actually, it means here that we are targeting a gene that is not a therapeutic one, but is actually just producing some light, not directly. But here, this is a luciferin gene, and by actually doing this, the goal is to show that if your cell is actually expressing the luciferase gene, you're trying to block this by the sRNA against the luciferase gene. And this is something you can monitor if you have actually a decrease of light emission upon treatment with the sRNA against the luciferase. So here we have a model of pulmonary metastasis in the mice, and the progression of the metastasis is directly observed by an increase of light when you have this luciferase expression and bioluminescence in here these conditions. And interestingly, you can see that we decrease this production of light only in the case of lipoplexes bearing the luciferase sRNA and also the HA covering, which means that here we have an efficient system able to really direct the sRNA into the cancer cells and having an intracellular delivery, efficient intracellular delivery to inhibit the luciferase. This is something that we've also been able to monitor at the level of the gene expression, where you have here a decrease in PCR observed of the expression of the mRNA. So this is a good proof, a good example of a study you can perform over the course, for example, of a PhD study to show how you can deliver efficiently sRNA in vivo. Now, what about clinics? What about clinical applications of these? Well, actually, the first example of a successful observation of RNA interference in clinics was provided by the Davis groups at the Caltech in the early 2010. And here what they have done is they have designed this interesting nanocarrier system. So it's a little bit different of the lipoplexes I just presented. It's looked like more a polyplex, because here the core that you can observe is a polyamine core. This is actually this in green, and the core is condensed with sRNA, so that makes a polyplex inside. And I like the chemistry of this system. Let me just tell you this in just 1 minute. I think they have used a quite clever way to functionalize these particles, because sometimes it's quite challenging to have, okay, you have your core, the polyplex, and then how do you put PEG on this? And what's more, how do you functionalize with the targeting ligand those extremities of the PEG? So here they have performed an interesting supramolecular organizations where they use the cyclodextrin adamantane interaction. Here they put some cyclodextrin at the extremity of the cationic polymers, okay? And that means at the surface of the particles you have those like a plug, okay, which is available, this cyclodextrin. And then to functionalize the particles, you just need to use adamantane covalently bound to a PEG, and that goes directly into the cyclodextrin. It's a way to directly plug PEG onto the surface of an existing polyplex. I found this very clever. And if you want to put a targeting ligand, then you just replace adamantane PEG by the adamantane PEG transferrin construct here. So this nice system was loaded with an sRNA and tested in vivo in patients. And actually they found some interesting effect on the melanoma, against the melanoma. So it was done only on a few patients, but you can see a significant decrease of actually the level of mRNA, which translates into the decrease in the presence of the protein inside the cancer cells. So it's a small scale study, but it was the first evidence of RNA interference in humans. And actually, a few years later, there was actually the first drug, okay, that was really approved for this kind of RNA-based therapy, which is the patisiran. And this was approved actually in 2018 using lipid nanoparticles. So here, those particles are a little bit different. I will show you the structure right after this. But it's still the same idea. You have the lipid-based particles, pegylation, and the sRNA in the core. This was done interestingly, to treat a disease that was really an orphan disease, okay? And that, I think, also is an interesting message. Sometimes it's possible for the industry to tackle other challenges than oncology, provided there is enough support, and that was the case here. And the disease is a hereditary transthyretin mediated amyloidosis, okay? So it's a disease in a small number of patients, but which is caused by the accumulation of a dysfunctional protein. And after treatment of the patients with an siRNA against this specific gene, a specific mRNA, you can see here a significant reduction in the production of the protein compared to the placebo. The way it works, actually, it's interesting because in terms of targeting, it's a little bit more complicated than what I just presented yesterday, because actually the targets are hepatocytes. So you could think that just preparing some first generation nanoparticle would be enough. For some reason, it was not the case, but they have done some particles that are thought to take ApoE, apolipoprotein E, within the bloodstream, and which is supposed to actually lead or to target the hepatocytes. So it's really a combination of the different targeting mechanisms I presented yesterday, actually, but it's quite efficient to deliver siRNA into hepatocytes. So that's a great example, actually, of successful translation of all these concepts into a drug. But that's a drug that is really restricted to a few patients. And actually the next milestone in the field was, right? That's the mRNA-based vaccines. So we're in 2019, okay? You've heard about COVID, you lived this, I think. And this came as a big application for the delivery of nucleic acids. So now we're not talking about siRNA, we are switching to mRNA. But actually the formulation strategy and the endosomal escape, the cellular intracellular strategy is really the same. And this is actually very a basic slide here just to discuss why we use this type of strategy for the vaccination. It was not the only one investigated, right? There had been some virus-based vaccines, okay? So that's just weakened and inactivated virus, which is not, of course, preferred for the safety, and especially at the beginning of the SARS-CoV-2 infection. You can also have the use of viral vectors, okay? So that's really what Claire has presented to you. And there has been some success in the vaccination against the COVID. You can do also some delivery of a protein, right? You take the protein, the more relevant protein of the virus, and if you deliver only the protein, it's supposed to be safe because there's no virus, and you can train the immune system to recognize here the protein. So the protein which is interesting is the spike protein, which I'm sure you've heard of. That's the protein of the SARS-CoV-2 virus that allows it to enter, to infect the epithelial cells. So there has been some attempts to formulate this protein and to produce some virus-like particles to improve its efficiency. However, this has not proven very successful for some reason. And in terms of vaccine development, it's also interesting to note that it's quite challenging, especially if you look at the emergence of variant of the infection. Because upon the emergence of variants, you may have some very different proteins that are produced. And if this protein happened to change just a little bit, just a few amino acids, but if you have a complete change of the structure of the protein, it may mean to completely reformulate and make another production of the protein, and that makes it very difficult to update as a vaccine, which is not the case for nucleic acid-based vaccine. Actually, The principle is a little bit more complicated, but however, you will see that it's actually much more robust and can be updated much more easily. In this case, and I'm sure you know that, the aim is to have the cells of the patient produce the protein of interest, the spike protein, which will be then released from the cell and used to train the immune system. And to do that, you could you could use DNA, but again, this is very challenging because you need some physical means to introduce the DNA within the cells. Whereas for mRNA, you can use a drug. Okay, this can be an injectable suspension of nanoparticles, and if you play, as we've seen before, with a proper formulation that allows an endosomal escape and a good availability of your messenger RNA within the cytoplasm, then the cellular machinery can just be used and actually diverted, if you want, to produce these spike proteins that will then be either released, we don't really know exactly how, but released by the cells to trigger the immune response. And by the way, this can be also produced by different cells. We don't always know or control exactly which type of cells will make this production, but it can be at the proximity of the injection site, which is intramuscular. The nanoparticles that have been used for this purpose are lipid nanoparticles, and there are actually many ways to really make them, actually to just draw them. I would say we don't always really control so far the exact structure of the lipid nanoparticles. In our experience, actually, when you produce them, you can get a mixture of different structures. Okay, so it's still debated today. But what is sure is that when you perform this formulation, you basically use most of the time the same type of excipients. You have the phospholipids that really make the structure, the mass of the particles. For example, here the SPC. You have cholesterol that helps the structuring the membrane. You have PEG lipids, okay, that allow you to cover the particle with PEG. And you have, of course, the ionizable lipids that we've discussed previously. By the way, why do you think we need to pegylate the particles? Why do you need to provide PEG at the surface of the particle? It's not intravenous, right? You don't administer this intravenously. You don't need to escape the hepatic recognition. Well, actually, I don't have a clear answer for that. I'm not even sure that PEG is really mandatory, but I think PEG has been widely used for the production of this type of particles, and for sure they help maintain the colloidal stability of the suspension of nanoparticles. So, to me, I think it's more of a habit, you know. And our latest results in our team show that if you can actually decrease this amount of PEG, it leads to interesting results in terms of targeting capacity. But for now, let's leave this question aside. And okay, all the formulations contain PEG and are pegylated. Okay. Another difference, or actually an actual difference between the mRNA LNPs and the siRNA LNPs is that you have much less copies of the nucleic acid per particle. And this is because actually here you have a 100 times longer strain, RNA strains, compared to the siRNA or the oligonucleotides. And there is an estimation of 1 to 10 mRNA copies per nanoparticle in this formulation. The way those nanoparticles are produced is actually something similar to what I showed you before when you have the ethanol injection within an aqueous phase, although with a little bit difference here. I'm sure you've heard about microfluidic mixing, which consists actually in mixing two phases that are miscible in actually some very tiny channels. And that is actually interesting to have a very rapid and very intimate mixing of those two phases. And typically to produce LNPs, we mix an organic phase made of ethanol, okay, containing all the lipids. And here you can really play on the ratio. You have the cholesterol, the lipids, and also the PEG lipids. And you mix this with the aqueous phase, which contains actually the messenger RNA. And controlling the pH is important to ensure that you will have a good ionic complexation between the cationic lipids and the messenger RNA. Nanoparticles are produced very rapidly upon the mixing, actually. And if you're doing this into fast enough conditions, you may have some quite small particles, which are around or below 100 nanometers. Then there is this important step of removing the ethanol, removing the solvent, which is now commonly done, especially in the lab, by using filtration. Okay, it's like this can be done easily at small speeds. So, of course, when you do this at an industrial scale, things are a little bit different. You can either make a parallelization, multiplication of those microfluidic mixing, or you can have also some more, I would say, conventional tea mixers, for example, that can be at a larger scales. There are several ways to do that, but in both cases, you can produce this type of LNPs. So here, we have shown them here with some pockets inside, which is also the type of structure you may get. So what are the results of this? How does it translate into clinical applications? Well, actually here I just put the first results. Sorry, those are in French because they're actually the very first results that we got in 2020, actually. Those are actually the first results of the Pfizer, BioNTech, and the Moderna LNPs. Which were a huge, a huge surprise and a huge success, immediate. If we compare both, actually, you have seen that the two cationic or ionizable lipids are a little bit different, but if you really look closely at their structure, they're actually quite similar. The ratios of the lipids are a little bit different, of course. And actually, the main difference is probably the dose of mRNA, okay, 30 micrograms versus 100 micrograms. And in both cases, the efficacy was really, really high, even if it was studied at small scale. And another difference in terms of formulation has been the conservation conditions, the stability. And that was actually a big difference because I don't know if you remember this, but one formulation was stable only at -80, whereas the other one was stable at -20, which made a big difference for the delivery to the patients. Okay. But actually, further studies have shown that those formulations were quite similar and could be stored in a similar conditions. But the thing is that we didn't have a lot of data at the beginning. It went very fast. We always teach students that it takes 10 years to develop a new drug formulation from scratch, especially in the case of vaccines, where you have to really, really ensure the safety of the populations that receive the vaccine. And in the case of the COVID-19 vaccine, this was achieved in 1 year and a half. Which was due to made possible by overlapping phases and some regulatory I would say adjustments. But actually, if we look at the milestones of this development, in early 2020, the complete sequence was released by the Chinese authorities actually, and the first clinical trials were started very, very rapidly. And actually, in December 2020, the first vaccines were approved, first in the UK and then in Europe, actually with a slight difference. And as of 2022, there were 10 billion doses delivered. And if you think of where we were in 2019, 2020, and we had the success of patisiran. We knew that we could deliver LNPs to patients on a small scale, but I think nobody imagined that a few years later we would have 10 billion doses delivered. And I think this is really striking, even for those of us working in the field for decades. Actually try to find some more recent figures, but there is the figure of 14 billion in 2024, but I actually couldn't verify this figure, so it's not for sure. But it's enormous, right? And another milestone to me also was that in 2022, you have also the approval of bivalent vaccines. Remember, we said that updating a vaccine is quite challenging. In the case of the SARS-CoV-2 infection, you can see the emergence of a lot of variants. And sometimes even a single change in a base can lead to a complete different structure in the spike protein and a different profile of the virus. It would be very difficult to make a different protein synthesis, but it's quite easy actually to just change the sequence of the mRNA that you put in your LNP. It doesn't change the formulation or the production. It's just a change then in the process of approval and evaluation, but the formulation itself is very easy to update. And actually this bivalent vaccine was actually a mixture of the original strain and the Omicron variant. So then there's been, a lot of questions about how fast this is going. I don't know if you or in your, maybe your family or the patients you may see if you're a pharmacist, there's been a lot of concern, right, about why this is going very fast. Is it safe, right? And actually there are many answers to that, but from at least the pharmaceutical technology point of view, I think it's important to stress that it's not so new, it's not so rapid. We've known, well, liposomes for 1960s, and actually the first development, or the first time you put some mRNA within liposomes can be found in 1978, right? It's quite some time ago now. And actually the clinic also, there had been, and that's important, clinical trials as early as 2014. So LNPs with mRNA, but that was mostly for anti-cancer applications, okay? But it also means that there is some background, there is some results, especially in terms of safety for this type of formulations. And you can see here the patisiran, okay? And all of that was a strong basis for the mRNA LNPs for vaccination. Also, the latest results in terms of toxicology are quite recent, but at least I've just checked the data from the French authorities, and there had been some cases, right, of side effects that have been sometimes even fatal side effects. We're talking about thrombosis, okay, which was especially the case for viral vaccines, but some cardiopathy, right, myocarditis cases were also reported, and some of them fatal, so and related to the vaccines. But that was very rare examples, and I think what the most striking figure to me is this more than 10 billion figure, right, of injected doses, which means that, okay, there had been some side effects and some fatal, but that was really a small and tiny fraction of them, which, by the way, seems to be related to the production of the protein itself, the spike protein, which may be the cause actually of the pathology and the fatal pathology, the myocarditis that have been observed. Okay, do you have questions on this part? Yeah.
I have a question going back to the beginning of your presentation. You talked about stiffness of a particle as a feature that it's been measured, and I was wondering, how do you measure stiffness of a nanoparticle?
So I don't know exactly how they've done that in this specific study, but usually the easy answer to that is to use some atomic force microscopy. You know the technique, you have a cantilever and you basically probe the surface of your sample. The sample is nanoparticles that you have previously deposited on this that can be more or less hydrated depending on the type of AFM you use. And the probe is actually so sampling the surface and can be used either for imaging, if you maintain a constant force that gives you the topology of the surface and you can identify your nanoparticles. Or you can choose to stay at the surface of the same particle and then record the force and see a deformation. And that's one way to have access to the stiffness, which may be expressed as Young's modulus. Right? I don't know, Nicolas, if you want to. That's okay. So that's one way to do that. And then you have some the values that can be really the Young modulus can be really different if you compare stiff PLGA nanoparticles or chitosan-based nanogel, for example. You can see very different the ranges.
So is then stiffness like a very decisive factor if you want to engineer the nanoparticle?
So that I don't know. In terms really of application, I think it's I don't really have the answer. You can correlate this to how the cell will respond to this. You can correlate this to how well the absorption profile may be influenced. But upon really administration, I don't know if we have enough data to really say that this is a really key parameter. But I think it's key really to the process of interaction between the particle and the cell. Yeah. I had just planned a few slides for toxicology purpose, just for you to have a few notions of that. Is it okay? Can you handle it until maybe not one, but just before? Is it okay for you? Yeah. So this is just for toxicology. I think it's important just to tell you that there is this field that is really important of nanotoxicology. Okay. So Nicolas already showed you a little bit of our studies in our lab, where we have performed some nanotoxicity studies, especially related to the lung region. So here I just wanted to mention some specific parameters that are related to nanomedicine. They are actually related. What is important to start with is to really acknowledge that nanomedicines are evaluated first as drug, okay, as drug products. So you have to evaluate this benefit and risk ratio, just like any drug product or candidate drug product. But then the question is, can we really identify some critical parameters that are specific to nanoparticles? The first one is the one we have encountered when we discussed what can be found in the lungs in the case of polymeric positively charged nanoparticles. Remember, if you have aggregation within the bloodstream, it's just the same as if you were injecting some very big particles that would block the capillaries. And this is something you can really evaluate pretty easily by characterizing the colloidal stability of nanocarriers upon injection, or in standard media that will mimic the injection. Another important parameter is the biodegradation and the in general biocompatibility profile of the excipients you use. Liposomes, lipoplexes, LNPs that use phospholipids are really on the safe side for this, because phospholipids are really something that can be processed by the cells and reused by the cells, so that's not a big deal. However, we should mention here that PEG phospholipids is raising now a few questions, because there is sometimes some immunization against PEG that is observed and may lead to the accelerated clearance then upon several further injections. So that's something maybe to take into account. For the polymers, as far as they're concerned, we try to use as much as possible biodegradable polymers, okay, which is especially the case for PLGAs, cyanoacrylates, and natural polymer, even if in this case, if albumin is produced, depending on the origin of the production of the protein, you may have also other questions. And also something I think to take into account is if you're using some hydrophilic, smaller polymers that can be excreted through the kidneys, it's also something that can be on the safe side. Then, because one of the first mechanism of elimination of the particles inside the bloodstream is by the complement activation and the recognition and the elimination by the Kupffer cells, you need to ensure that the particles you administer to your patients will not overflow the system or will not limit its ability to defend against, I would say, legitimate threats to your body. So this is something you can study by looking at the elimination of standard carbon particle that can be administered right after exposure to nanoparticles of interest. And you can see, for example, here that there is a limitation of the capacity of eliminating carbon particles after exposure to higher quantities of nanoparticles. But this capacity is recovered pretty rapidly here, in this case, after 24 hours. And this kind of study you can also perform to look at the complement activation capacity. There is this one important side effect that has been observed several times, which is called the CARPA effect. The CARPA stands for the complement activation related pseudo-allergy. This is similar in terms of allergy because of this massive reaction. However, it is not like an allergy because this occurs when it occurs at the first administration. And I say when it occurs because it's very, very rare, but when it happens, it can be fatal. And this has been observed not only by looking at nanomedicine such as liposomes, but also with micelles. And this, for example, is, it's pretty standard excipients that is used for the hydrophilization of very, very hydrophobic compounds, anti-cancer compounds, such as, for example, paclitaxel, docetaxel, so quite common, and even observed sometimes in the use of contrast agents. So this is now, there is quite a lot of research on that, and actually the need to develop some predictive tests also can be something of improvement to prevent this. And also then the specific recommendations that apply to the nanoparticles. That is something I've just told you before. And also some consensus that now is used as a precaution is, for example, when we test a totally new nanomedicine, we look for potential allergy in patients, and you can perform some pre-medications, slow injections, and as I told you, try to look for predictive tests for this specific reaction. So to conclude, and that will be my last slide, I think it's interesting to see those two different types of application when you are doing some either targeting of the cells and tissues, or really looking at the interaction at the cellular level, which is really key to deliver some sRNA, mRNA. And if we make really to wrap this up today, we can see how basic concept 50 years ago has really led to nanotechnologies and to really use the technologies today. We discussed, the number of nanomedicines on the markets, but it depends how you count that. But I think what is maybe more telling is that today you have some generic formulation, and that especially the case of Doxil, and many countries, now several countries produce some generic formulations of this Doxil. Increasing the efficacy is really, of course, what we all want to do, but increasing the tolerance, I think, has been almost and maybe more important in the clinical success of several nanomedicine. And in the case of nucleic acid, if we okay, if we leave the electroporation and if we leave the virus aside, if we really look at pharmaceutical formulations based on excipients, we can say that it really enabled the use of nucleic acid and therapeutics based on nucleic acids. And I think that's only the beginning. Okay, so if you have questions, I'll be happy to answer. Thank you. Yeah.
Me gustaría, muchas gracias por la presentación, por los 50 años de revisión. Quería preguntar desde el punto de vista de la interacción con otros fármacos, ¿qué se sabe en el uso de nanopartículas?
With conventional medicine? Right. Well, that's a good question. Never thought about this. I don't think there's a clear answer in terms really of how the formulation itself, you know, because I mean, nanomedicine really depends on what drug molecule you put inside. I don't have any examples of any potential interactions or really related to the nanoparticle itself. That's a good. I don't know. I will look for that. Yeah, that's good. Do you have any ideas? No. That's a good question. Look for that.
Tengo una duda respecto al self-fractionation method. ¿Cómo se realiza el estudio?
Which study?
Self-fractionation method.
Oh, self-fractionation.
He's an expert.
Yeah, well, so here the goal is to identify which fraction of your particle is at the different subcellular compartments, right? So first you need to have a detection method. Usually it can be done either by radioactivity or most conventionally by fluorescence detection. So here it's important to know how your probe is really attached to your particle. Is it attached to the particle itself, to the polymer? Is it just associated to the particle? In which case it's important to really ensure of what you're really following. Okay, so that's the first thing. And then the process itself consists in progressively attacking the cell, if you want, okay, to use some detergents of increasing strength. The first one is just a protease which actually only eliminates the fraction of particles merely adsorbed at the surface, and this can also be done by washings, repeated washings. And then so you collect this and you measure it, if it's recent, for example. Then the second step is digitonin, which makes small holes in the cell membrane, and you get the fraction that has already gone through the escape of endosomes, right? Then the next step is an increased, I would say, detergent with an increased power, which is Triton, and then you can collect really the fraction that was so at the intermediate stage in the endosomes. And then what you get is something at the end you really collect usually by centrifugation, the debris, cell debris, and things that are associated to the debris might be, for example, stick actually to the internal organelles. Okay, so you can do this by it requires a little bit of optimization, right? And this is something that you can do. For example, you really need to actually optimize the conditions between the Triton and the digitonin. And to do that, you follow the recovery of enzymes, the catepsins, and another one here, LDH, I think, which are actually representative of both compartments. But it's also good to know that there are some kits that are available for specific cells. Okay, a bit expensive, but that exists.
¿Otra consulta?
Muchas gracias por la presentación. Yo quería hacer una consulta sobre si hay algún
font les tests de biocompatibilité et de biodégradation, un peu réglementaire.
That's I don't have all of them. I can look for that. Degradation.
I think there are some tests in the pharmacopoeia for biocompatibility, but I don't remember exactly which one. And for biodegradability, I don't know if it's standardized yet.
Yeah, I don't think it is. Usually, what we do is we like to use some excipients that have this track record. You know, there is this GRS, generally recognized as safe, for the FDA, which is a good repository to select excipients from, or then excipients that have been studied in formulations, in existing formulations. So it means they have passed through the regulatory process. This is generally how we proceed. It's pretty rare that you have a totally new excipients, but I don't know yet if there are some really standardized tests. I'm not so sure.
I think for biocompatibility, for implants, you have to inject them subcutaneously and see there is no fibrosis, no inflammatory response, things like that. So I don't know for nanoparticles if you have to do the same thing also. For the moment, I think that at least at the European level, there is no clear difference between nano systems and normal drugs. So I think you use the same test that you use for normal drugs for the nano systems.
How you calculate the lethal doses about a drug that don't have a specific target, you know, because your focus is not log a specific receptor, you know, in the case of your show.
So lethal doses, you mean?
Yes.
Yeah. I think when you measure this type of doses, it's global response, right? This is something you measure on the animal level, so you don't even need to consider or the mechanism. You see? Yeah, you don't need to consider this mechanism. You just measure a little dose. Then what you can see, if you're referring to maybe the higher tolerance of the nanosystems, I think it's more an understanding of the dose increase that you can do on the clinical phases, right? That's really where you can really see the difference in terms of tolerance. But this is different from the lethal doses. This is pretty, I would say, very unspecific test, right? That you use, I think, more to characterize a substance itself, or excipient or drug substance itself, rather than a whole formulation. I'm not so sure you would do that on a whole formulation. Yeah.
Bien, si no, agradecemos a Hervé y Claire también de la encontramos a las 3 de la tarde en la Facultad de Farmacia.